Check, check. Testing 1, 2.
Hello, test. 1, 2.
So this one's yours?
No, we got to give one to him. Or intros? Okay,
Yes.
that's fine.
The questions I can run them.
Okay, so this is off then.
Correct.
So we can put. All right. All right, folks, I think we should get moving. Welcome to the second day of our RCN meeting. I hope you enjoyed the wonderful dinner last night and also had a good day of discussions and technical discussions and brainstorming. And I think today would be, we'll build on that, and we'll start with our second keynote, Professor Ted Rappaport, and I'll introduce him in a second. After that, and he has to catch a flight, so he'll be leaving soon after that. But then from 9 to 10, we'll have a readout from the breakouts yesterday, from the 3 breakout sessions. And so that's going to be seeding the panel 2 discussion. And panel 2, we're going to be improvising. So Ozge will be here. Michele, I always mutilate his name, is here. And then we'll have some of the breakout leaders on this panel discussion as well, discussing some of the breakout issues and what we can do going forward. In particular, test beds in relationship to power would be one of the important discussions. Okay, so, well, it's a pleasure to have Ted, Professor Ted Rappaport, giving our keynote today, and he clearly does not need an introduction in this community, certainly, and probably much wider, but he got all his degrees from Purdue, but we won't hold it against him. And he's a distinguished, well, you know, the joke in Urbana when I was going to grad school there was that the only consolation about Urbana-Champaign is that it's not in West Lafayette. So, you know, the Purdue people would come there to party. And he has, he has had a tremendous career, and I think he's a professor in 3 different departments here. He's a chaired professor, and he has a singular accomplishment of starting 3 research centers, really successful, very visible, every 10 years almost, like starting with 1990 in Virginia Tech, and then 2002 in Texas, UT Austin, WCNC, which is doing great too, and then here in 2012, and here we are. And yesterday we had the father of DSL, and today we have the father of 5G millimeter wave giving the keynote. So, and you know, he's had many, many awards. I can't even list all of them. And clearly, I think for millimeter wave, there's no question. I think he has been instrumental in bringing it to the forefront of industry and you know, government regulators, FCC, to really move the things forward. And I remember at the 2016 announcement when NSF announced the 400 million wireless initiative, right following the FCC announcement, which was the day before, Ted said, "Oh, this is a double rainbow day." And, you know, and he had a video, so all of you can go and Google double rainbow and you'll find. And you know, I'd probably seen double rainbows before. I'd never paid attention, but since then I've seen several, 2 straight out of my front yard. So thank you, Ted, and please come on and give us your thoughts. Thanks.
Thank you. Thank you very much, Akbar, for that very nice introduction. Thank you all for coming early this morning. Sandeep Rangan, thank you for hosting this event here at NYU. And to the staff, Pat Donahue and Campbell, Taylor, Busfield, and Adam Holston, thank you so much for all your efforts this week. I'm very happy to be here to talk about 5G millimeter wave, and I'd like to cover 6 points. First, I thought you might enjoy kind of a backstory of what happened and how my students and I figured out that this 5G millimeter wave would work, and some of the trials and tribulations we went through and some of the discoveries we came up with back about 4 or 5 years ago. And then I thought I'd present how those differences have kind of developed over time and how the 3GPP global standard has evolved in the area of channel modeling, and I thought I'd do some quick comparisons because it turns out that the channel model is vital to comparing and testing, and we found some distinct differences, but because of the breakneck speed of this development for 5G new radio, probably the fastest standard development in the history of wireless, is 40-year history, to move up an order of magnitude of frequency. I thought that'd be interesting. And then I wanted to look at some real-world issues and some things to consider in the area of hybrid beamforming, comp, and development in general. And then I thought I'd touch on the trials, actual update of what I've heard from industry leaders who are actually doing the trials and what the results are. And then finally, I thought I'd look at some things that we don't often talk about in academia, but is very important to the development of new technologies like the internet, like millimeter wave wireless, and that is the regulatory framework and some of the things the FCC is doing to help speed the deployment of millimeter wave in the US. And these kinds of activities will probably be echoed around the world in other countries. And then I'll conclude. So this curve, it was really interesting. Yesterday, a number of presenters talked about hype and where things are and what's real and what's not. And this is a very useful curve called the Gartner hype cycle. Gartner's an information, kind of an analyst that's very highly regarded in the technical field. And this is the Gartner hype cycle curve. They publish it every year. And on the x-axis, it's cut off on this slide, but on the bottom, you have on the left the technological trigger. When something is triggered by a fundamental discovery or a basic new issue that's come up that people haven't thought about before. And so on the left, you have this innovative trigger. And then here at the peak, this is maximum hype. And then you go in time, a few more years, and then you fall into this trough of disillusionment, where all the hype seems like it was overblown, and it's actually not going to work well. And then as you go to the right, you kind of hit this slope of productivity, where people get over the disappointment and then just get to work. And then here you finally taper off to where it really becomes real and productive. And this is basically the utopia. It hits mainstream and everyone wins who stayed with it. And you can see here we are at the 2017, maximum hype was deep learning and machine learning. And all of you in electrical engineering know that your enrollments are going down in the hardcore electrical engineering because everyone wants a job in deep learning, machine learning, and all the salaries are there for all the stuff. And now pundits are saying, what is everyone going to do in 2022 when that entire market busts? So we're at maximum hype now. And if you note the color, it says, well, in 2 to 5 years, it'll actually start being productive and on the slope of productivity. But right now, it's full hype. What's interesting is 2017, 5G wasn't yet quite in the maximum hype cycle. It had 5 to 10 years to go before it was real. So I suspect in 2018, 5G will be here in the peak of maximum hype, and then maybe machine learning and deep learning will fall off. You know, and then it'll go through a trough. But what's interesting is autonomous vehicles, self-driving cars, right here near the maximum hype in 2017, and it's still a lot of hype. And then you have the terrible accident with Uber, and it starts heading down into the trough of disillusionment. But it's always interesting to look at this. And, you know, it's good to see 5G's here, and even business analysts, which don't always get it right, are saying 5 to 10 years. So they're saying 2022 to 2027 is when 5G will be building out. And I say that's probably closer to 2022 than 2027. I'd say it's probably 2020, 2021. But it's always fun to show. Now, how did we get here? How did we get to millimeter wave? We have NSF doing these workshops. We have the FCC making spectrum. We have probably tens of billions of dollars being invested around the world in various areas of 5G, even when 4G is still building out. 4G is an amazing generation of technology. It allows smartphones and applications like Uber and real-time video, and probably some people out there on the internet watching the real live stream or watching this on 4G. Well, here's how it happened, and I thought you might enjoy the backstory. I was at UT Austin and had done measurements at 38 gigahertz around the campus. In fact, let me go back 10 years earlier. At Virginia Tech in 1995 and 1996, I was looking at 38 gigahertz. I actually published a paper on what hail and rain do to fixed links, because this was before the LMDS, the CLEX, the idea of independent local exchange carriers putting up millimeter wave. Companies like Telligent went public at unheard of valuations in the late 1990s, and a few years before that, I was showing that you could do millimeter wave communication with huge bandwidth, and that weather wasn't that much of a problem. I was doing that at 38 gigahertz. But it became very apparent to me that the semiconductor industry back in 1995 just couldn't make the devices cheap enough, and we didn't really have the internet yet on cell phones. So the idea was way too early. So I kept the equipment in mothballs, always checked it out every year or two to make sure it worked. And then in 2011, as WiGig and wireless HD in the 60 gigahertz band for Wi-Fi was ramping up, I said, now's the time to go mobile. So I did measurements at UT Austin in 2011 and actually saw amazing coverage, non-line of sight coverage, which really surprised me. And when I came to NYU, they said you could get on every roof, because I said, if I'm coming to NYU, I want to make millimeter wave tests and show the world this can work. They said, okay, we'll let you get on the roof. They don't like to do that generally. So I had rooftop access in New York, and I figured if we could make it in New York, we can make it anywhere. And so we put base stations up in 2012 and had a team of undergraduates, freshmen. They just finished their freshman year in college from the CS and ECE departments. And they worked tirelessly, and we made measurements all over Washington Square, on the business school rotunda, on the courtyards, went all around the streets of NYU. And lo and behold, indeed, it was working, and it was working really well. We made a channel sounder that used a sliding correlator method so that you could get very good dynamic range, 140, 150, 160 dB path loss, with very wide band, 800 megahertz RF bandwidth, yet you could get the advantage of time compression so that you could get the multipath, but you'd use a dilation, time dilation, use a sliding correlator, so you get these large link margins with relatively low power. So we're using 1 watt of transmit power at 28 gigahertz, 800 megahertz bandwidth, and getting very comparable base station-like ranges, in fact, much less than what commercial base stations will use. And we published these papers in 2013, and I'll tell you a little story about those later, but the bottom line is we started to collect huge amounts of data. We measured Brooklyn, we measured where you walk coming into this building and on the courtyard of Brooklyn. We had huge amounts, terabytes of data over the next few years. And one of the amazing things is we collected all this data using directional antennas. There's a channel sounder right out here running at 140 gigahertz that my students are using, very similar architecture. So we would just meticulously scan with directional antennas. And what we quickly saw is that with all this directional data, there was a lot of confusion. How do you process all these little narrow slices of received energy over azimuth and elevation in different locations and make sense out of it? How do we do an impedance match or a conversion to language that the wireless industry would understand? So here's what we realized. The entire wireless industry in 2012 viewed the world as omnidirectional at the handset. In fact, the entire wireless world viewed wireless in general as kind of omnidirectional. A base station, even if it's sectored, was kind of viewed as an omnidirectional antenna, and a mobile was viewed as an omnidirectional antenna. And so when I go around and tell people in 2011 and 2012, often I was scoffed at when I said millimeter wave would work. I realized after collecting all this data that people were misinterpreting a common law which is fundamental to wireless, which is Free's free space equation, this equation right here. And what I realized is the whole world was looking at Free's free space equation, which tells you the received power over the transmitted power is equal to the product of the gains of the transmitter-receiver antenna times this lambda squared over 4 pi d squared term. What I realized is everyone was thinking that GT and GR is 1. Unity gain, omnidirectional. And so what I realized is, my gosh, what we're doing is when we use a directional antenna at the transmitter, it's not 1, but it's AE, the effective aperture. It's kind of like the physical area times 4 pi over lambda squared. And what we're doing is we're canceling out the lambda squared in the numerator here with a lambda squared in the denominator there. And so really we have the gain of the receiver antenna over d squared. So everyone says, gosh, we have this terrible higher loss at millimeter wave because as lambda goes down, down squared is up, so the loss goes up, all right? So everyone views the loss as being greater at millimeter wave, but our data said it wasn't. And I knew from this formula it wasn't. This is the biggest misconception still to date. And this is why I want to bust this myth. Millimeter wave is better link margin, more received power than we've ever had in wireless. And here's the math. People, at best, would figure out, okay, if I use a directional antenna, I could at least get rid of one of these lambda squareds, but I still have the 1 over d squared loss. But here's what happens when you use both the gain of the antenna and the receiver. You get a lambda squared in the numerator, you get a lambda by 4, a lambda squared squared in the denominator. So you basically get a gain. You actually get a gain from the antennas that can beat the d squared loss. In fact, if you use a constant physical area on the cell phone and a constant physical area at the base station, that is A sub E stays constant, and you change the frequencies in both these terms, you get a square increase when you go higher in frequency. And this is why all the world is surprised and shocked. The trials are better than we ever thought. Well, of course, because you get a much better link when you keep the area the same but go higher in frequencies, because you're basically getting more focus. And the math shows it, but the world doesn't even still today understand it. In fact, let's look at the simple case where maybe you just put gain at the antenna and you keep the receiver shrinking as you go higher in frequency. If I keep the receiver on the order of lambda, that is A sub E is lambda squared, look at the gain of the receiver. Lambda squared over lambda squared is 1, and I get a 4 pi term. So basically, if I keep the transmit area constant as I go higher in frequency, and the receiver gets smaller and smaller, which is how the world always thought of it. They'd always say higher free space loss at higher frequency, because in their mind, they don't realize that they're shrinking the antenna as they make that proclamation. But if you keep the receiver shrinking, but the transmitter constant, the 4 pi squared cancels out, the lambda squared cancels out, and you get the same received power over all frequencies. So at worst case, if you shrink the receiver, you still get the same path loss. Now, I'm not counting weather or hail or fog or foliage or trying to get through building walls. But the bottom line is in free space, you actually get better signal-to-noise ratio. This is a fundamental result that the world is still trying to grasp. But the transmitter-receiver area, if it stays constant, if you use the same real estate on the tower and in the handset, the received power is greater at higher frequencies than lower frequencies. Now, how do we figure that out? How did we prove it? We had to do a lot of processing, and this paper in GlobeCom 2015 has kind of become the standard by how everyone processes this directional data and tries to put it in a way that we can all understand, and particularly what 3GPP understands. 3GPP had always made omnidirectional path loss models. You put the gain of the antennas on after their path loss model. It's how all the generations of cellular developed. But we figured out that it's vital to get rid of the gains in a way that's fair to what's happening. That previous slide is when you have a direct link, kind of bore site aligned transmitter and receiver. When the bore site is aligned, that's a very special case. It's not a scanning receiver, it's not scanning beams, it's when you've done all that hard work and now you have the link. But in the real world, in statistical channel modeling, when we're trying to develop systems, we don't care about knowing where the exact link is. We want to know what happens for any case. And that's what the omnidirectional model does. So we figured out how to process all this data regardless of the antenna gain so that you could rescale everything to an omni model and then change that back to any antenna pattern you wanted. And that's really tough. And 3GPP is still wrestling with that. And here's some of the fundamental things we found. While 3GPP was rushing to make a channel model so it could develop 5G new radio, they were really doing it without very many measurements in the world. They had our measurements, which we provided and published aggressively so they could see it. And we helped them build channel sounders, our industrial affiliates. We worked closely with them, gave them software, hardware, told them our vendors. So a lot of the channel sounder you see here at NYU is reproduced very rapidly by teams of engineers all over the world, the companies that build the 3GPP standard. They went out and found the same things we did. They proved it to themselves in 2014. And we launched the Brooklyn 5G Summit here as a place, a melting pot, for all these people to come together, to bring the FCC, to bring federal regulators, so they could see what was happening. We hold that every year in April. And what we found is that, remarkably, the channel model that had been used for 2G and 3G, which was this floating intercept model that was standardized in the 3rd generation and 4th generation 3GPP standards, used these parameters alpha and beta that had no physical significance. But when you get to millimeter waves, because it's very site-specific, it's vital that you have a physical significance to your channel model. Otherwise, you can't make sense of what's happening with different directional antennas if you're on board side or if you're not. And so what we proved is that if you used the old 3GPP models, you could get these really bizarre slopes for path loss, which were very specific if they happened to be measuring and a building was blocking it. But if you went over 360 degrees and you used this physically based model, which used a free space path loss reference at 1 meter, that is, if you standardized everything to 1 meter, free space, close in, free space, you got an n value, a path loss exponent, that had significance, it had physical meaning. It went back to the original theory where n equal 2 is free space. In this equation, n equal 2 is the path loss exponent, that's free space, and n equal 4 would be a 2-ray ground bounce model, as taught in my textbook and taught in the 50s by Bullington. So we were able to show that there's physical significance when you use this very simple 1 meter universal free space path loss reference. And it was vital once you use the 1 meter path loss reference to understand directional path loss models, because n actually goes up. You get more loss in path loss exponent if your beam is not aligned. It's when your beams are aligned, and that's what we have to do in beamforming, align the beams, align to the best bounces, find the best multipath when we're scanning. That's when n goes down. So it was really important to have both directional path loss models and universal free space path loss reference. Now, this met with resistance from a lot of the industry. 3GPP didn't want to use a 1 meter free space because they had software written below 6 gigahertz. So they kept on doing the ABG model. But they did concede that this was better for millimeter wave, and so it actually made it into the standard. Shu Sun and George McCartney, 2 PhD students, were able to get the CI model into the 3GPP standard. I'd never had grad students during their PhD actually get a 3GPP contribution. So that was pretty good and an acknowledgement that the world was seeing that this is different. Now, there are other things that 3GPP did in the development of their channel model in haste. They basically took all the stuff below 6 gigahertz that were done with pretty much Omni or Omni-like antennas, certainly not with the beam width you need at millimeter wave, 10 or 20 degrees. They used broader beam antennas. And they basically took all the parameters for number of scatterers, number of clusters, time cluster, and brought that into the 3GPP standard. It was fast, it was quick, they'd all have a standard channel model to compare their algorithms with. Problem is, it was wrong. We had all these terabytes of data and we're processing it, and while 3GPP assumed there's 12 clusters and 20 rays per clusters, we were finding there's much fewer clusters. In fact, there's only at 6 at most, usually 6 directions, not 19. And usually, these are random, depending on where you are in the streets of New York or Brooklyn, and not fixed. And this is a problem, as we'll see in a minute, because if you have fixed number of clusters or paths or diversity paths, that basically means you have to build that many RF receivers to get all the energy, or have that many chains. Or conversely, it means that your channel has much more diversity than it really does. Turns out that 3GPP and the people at it are pretty wise, because they knew that wouldn't do a whole lot on capacity, and I'll show you that it doesn't. You get on the order of 2 factor of 3 dB in capacity using the different models. But where it does come into play is how to build a receiver, and I'll talk that in a minute. So here you had industry using this ABG alpha, beta, gamma model, which had 3 parameters, alpha, beta, and gamma, which are just path loss parameters that have no physical significance. And we used the close-in reference distance model, which had only 1 parameter. 1 parameter, this value of n right there, the path loss exponent. So 3 parameters versus 1 parameter with virtually the same standard deviation. In other words, the ABG path loss model was oversubscribed in terms of number of parameters. And that's why you got these really weird-looking curves in the ABG model if you happen to specifically measure one particular angle at one particular building or had one group of buildings blocking your measurements. Very much measurement dependent in ABG. The CI model, close-in model, is much more accurate. And it used this free space anchor at 1 meter and 1 gigahertz. Now, why 1 meter? 1 meter is pretty much in the far field of most millimeter wave mobile devices. But here's the other reason why 1 meter. And I never really expressed this till today. 1 meter wavelength is 300 megahertz, right? All the millimeter waves way above 300 megahertz. In fact, UHF cellular started above 300 megahertz. So lambda at 1 meter is 300 megahertz, is a frequency much lower than we use in millimeter wave. If you just put a lambda of 1 here, everything cancels out, and you see the point I made earlier immediately. If lambda is 1, you can immediately see that with lambda of 1, the gains, the a sub e squareds, come into the numerator. And so using a lambda of 1 meter, you very, very quickly can see the fact that your gain increases by the square of the frequency when it goes up. Another reason why is if lambda is less than 1 meter, you also see that very quickly. If you put a lambda less than 1, you get a less than 1 squared over a less than 1 to the 4th. What's a less than 1 squared over less than 1 to the 4th? Much, much greater than 1 squared. So again, you see that the gain's very quick. So this 1 meter has very nice intuition as well as being accurate. And so we also noticed in these field measurements over 28, 38, 73 gigahertz, now 140 gigahertz we're measuring, that while the industry and a lot of common models want to force the joint spatial and temporal cluster definition, we found that field measurements don't do that. See, here's what the channel model is in cost in 3GPP. They force an assumption that any multipath that happens in the channel model are both spatially and temporally joint distributed. That is, any multipath delay that arrives at a certain nanosecond delay must come from a particular angle. They force that joint distribution. That the angle of arrival, it happens to be also coming from a time delay. But we found in the streets of Manhattan that I could have a multipath at 10 nanoseconds coming from a nearby building, and at the same 10 nanoseconds, I could have something coming right behind me from the other building. So in that case, you have two rivals at one time delay coming from two different angles. So the joint spatial temporal model used by 3GPP and in a lot of textbooks is not what you see in field data. Actually, in field data, you see time delays coming at many, many different delays from the same angle. Maybe it's a building here, 300 meters away, and another building 500 meters away that's taller. The energy will still come from the same angle, many hundreds of nanoseconds apart. We saw this. And so we defined this definition of clusters, where you have time clusters, but spatial lobes, where there are no more than 6 spatial lobes, and there's many time clusters. We have the distributions. We saw it time and again. We processed all this data, and we call this the a time cluster spatial lobe approach. Now, the energy in space always has to be equal to the energy in time. The area under this curve is the area under that curve. Space and time energy is the same. But it's different. It's a different approach, and it's a statistical approach. So we made this simulator, NYU Sim, came out in 2016. FCC was interested in it to validate some of the things they were seeing. In fact, the FCC followed our work very closely. They would call me. Michael Ha would come up to our Brooklyn 5G Summit back in the early days, before the world believed. They really wanted to see if this was happening. And indeed, they saw it was real. They used the simulator. And it basically recreates all the measurements we've made. So you can get free, open source, downloadable in MATLAB, this simulator, NYU Sim, which replicates all of this. And here's some of the interesting outputs of NYU Sim versus the 3GPP channel model. Let's look at the eigenvalues of HH Hermitian, which is basically telling you the energy or the diversity paths, the rank you have of the channel. This is the famous Raleigh channel, which is why OFDM evolved and became vital in all 3G wireless. The beauty of having narrowband channels, narrowband tones, is why OFDM is so great. And we talk about it in Chapter 2 of the millimeter wave textbook that Robert Heath and I wrote with our PhD students. This is why OFDM happened. This is why we love it. OFDM is a bunch of narrowband channels. Narrowband channels are flat fading. Flat fading in any mobile environment is Rayleigh. And this is why we use it, because you can use MIMO in OFDM. Because you have all these narrowband tones that are all fading Rayleigh. That's the Rayleigh channel. In wideband channels, though, NYU Sim and 3GPP, here's what you have when you basically demodulate and are looking over wider bandwidths. NYU Sim has fewer higher ranked eigenvalues or channels. So we have like 3 main channels. 3GPP predicts 4 or 5 channels. So you can see that the rank in 3GPP assumes there's more diversity. The largest 4 eigenvalues you can see here. NYU Sim has fewer but larger eigenvalues. 3GPP has weaker but more eigenvalues. And this is going to lead directly to hybrid beamforming results, digital beamforming results, diversity results, signal processing. Now, we just published this paper last week. The new proof just came in. And this is kind of the definitive discussion of all of this, all of the channel models. And in this paper, we look at hybrid beamforming, we look at single-user MIMO, we look at multi-user MIMO, and we look at comp for a 3-cell base station from 3 to 12 users. If you're working on beamforming or comp, this is a remarkable resource. Just went online like 3 days ago. And it's basically a culmination of everything I've just talked about. The NYU Sim versus 3GPP and the result of receiver architectures and hybrid beamforming and comp. And I want to go into some of the results now of the 2 PhD students, George McCartney and Shu Sun, who helped bring a lot of these ideas to the world. So we've heard a lot about beamforming. We've heard, and I need to finish up pretty quickly here. We've heard a lot about beamforming. We've heard a lot about digital beamforming. And one of the interesting things is analog beamforming, which is right now being used in most of the trials, is very simple. You have a single RF chain. You basically have RF precoding a network that's going to do RF distribution to the antennas to basically get fixed beams. Digital beamforming is kind of the holy grail. This gives you maximum flexibility. You can put a beam wherever you want with amazing fidelity based on the resolution of your array. The problem is that you need a lot of DACs. You need an RF chain for each of the antenna elements, which right now, today, is expensive, and will be expensive probably for 3 to 5 years. So why hybrid beamforming? Hybrid beamforming basically takes advantage of baseband precoding and RF precoding, RF distribution, phase shifters, to kind of find the best of both worlds. You use a large number of antennas so you can get good array fidelity, but you can use fewer RF chains, less cost, less power, and it's very, very close to the spectral efficiency in a real system simulation that you get with digital beamforming. That is, you're like within 5% of the spectral efficiency if you go to the effort of all those digital beamformers. And so you'd start using beamforming with various approaches of comp, where today's cellular, we use a lot of these single cell and multi-user MIMO is where a single base station will send to multiple users. But comp is something that we've looked at in 4G, a lot of complexity. And so we wanted to kind of bookend what happens for a single user MIMO case, a multi-user MIMO case in a single cell, and what happens if we ever get to comp with best beamforming. So I'll just quickly give the highlights of the work. We all know what 4G and 5G is. And so basically, we're going to look at non-comp and comp using different beamforming architectures. And they're discussed in that paper I just mentioned that came out 2 days ago. And I think these are the world's first results of comp. First, we've got measurements we made on this campus. This is the map of our campus. And George McCartney, for an entire summer of 2016, took very high-resolution angle measurements, thousands of angular measurements from all these base station locations, and received them at the other locations. And we built this database. And the bottom line is, even with a high-density base station cluster, there aren't that many places in a mobile system where you're going to have a lot of interference. That is, maybe you could get 16% of the time in full interference, twice the capacity using comp. But most of the time, 43% and 35%, that's like 80% of the time, you rarely get capacity gains using comp. In fact, Shu Sun looked at the simulations, which are in that paper, and found the same thing. And by the way, these bits per second per hertz are kind of hypothetical. You know, it's hard to get 10 bits per second per hertz with modulation, but it's kind of a reference. It's a benchmark. If you look at this going 3-user and 12-user per cell, the NYU sim channel model predicts more capacity by about 25 to 80% more capacity. But the bottom line is comp's not going to give you a whole lot. This is baseline with a single cell just forming single beams. This is the best you can get with signal leakage noise. Akbar, one of your students, helped kind of develop this idea. And you can see that at the 90% point, you maybe get a little bit more using comp, but not a whole lot more bits per second per hertz. In fact, knowing this, the industry is now building out these trials, and they're not looking at comp, and probably won't be probably won't use comp, because millimeter wave is not interference limited. It's basically link limited. You don't have a lot of interference, which is what George's work showed. So here's what's happening in trials real quick. There's a bunch of trials in Texas, largest 5G trial at the silos. Attenuation by tinted glass is major. They have launched 5G already. There's 1 gigabits per second download speeds, less than 10 milliseconds latency, reported at 15 and 20 gigahertz. This is before the 5G NR. And they're going to be using standalone pucks that take the outdoor signal from fixed wireless and distribute it indoor. Verizon's going in 11 cities. They're going better than they ever thought they would, well over 1 gigabit per second, 10 milliseconds, and again, prior to 5G NR, which just came out last month. So trials are working. They're really excited. Intel's got a product which they call the mobile access unit, which they put right at the window and the wall. They take the fixed wireless access signal from the base station of 5G and then redistribute it using a hockey puck. Here's what it looks like. This is the wireless remote radio head. The station comes in from 5G, the fixed wireless access. It's then redistributed. They're getting 3 gigabits per second. And then the FCC, trying to ramp this, created this rule just recently, a few months ago. They asked our opinion. We gave it to them. We said, look, you've got to make it easy for the wireless companies to deploy. You've got to make it easy for them to get on lampposts. Right now, cities and municipalities realize they can charge money and hold up the permitting process for carriers that want to deploy small cells. They see this as a revenue grab, and the wireless carriers view this as a tax on mobile broadband. You know, if you're going to call it a tax, call it a tax. Don't hold up our business. So the FCC is trying to remove unnecessary barriers and trying to make it possible for small cells to be legally deployed without onerous rights. And we asked our industrial affiliates before we talked to the commission, what do you need? What do you want to see wireless happen quickly at millimeter wave? And here's what they said. It's got to be fast. They said the small cell order is a great first step, but we really need more mid-band spectrum, and they want these auctions happening. FCC listened. Auctions are happening this November, which I predicted back at the Brooklyn 5G Summit. Even though the FCC was hedging, they said it'll be next year. I said it'll happen this year. It's happening this year. You need to give them right-of-ways. These companies are desperate to get right-of-way on poles and lamps. They want to avoid zoning. They have to be reasonable. They can't put up ugly things. But this is a big deal. And then Michael Marcus, who's here, has helped propel this 95 gigahertz and above spectrum horizons. So in conclusion, 4G LTE, which we have today, is morphing into 5G. You won't see comp used. You will see multi-user MIMO and comp. Comp only gives you about 5 bits per second per hertz greater than uncoordinated. Is it worth it? Read the paper. And carriers have to decide, because right now I don't think it's worth it, certainly in this early stage. Maybe in 6, 7 years it'll be worth it. Interference is so much less of a concern with these directional arrays. That's why comp's probably not going to happen anytime soon. The myth busting I showed you shows that there's greater signal-to-noise ratio, greater data rates, and greater coverage as you go higher in frequency. Sans the weather, but you know, over a few hundred meters, rain's not an issue. I gave you some recent testimonies and stressed some key regulatory needs and the auctions that are now happening. And in conclusion, millimeter wave really is the tip of the iceberg. The FCC's gotten out in front on these issues, but countries all over the world, primarily in Asia, are working very, very rapidly on this. Finally, I want to thank the NYU Wireless Industrial Affiliates program. Qualcomm is here, Osgay. All these companies are great partners. We really work closely with them and take their inputs to the FCC. It's very harmonious and symbiotic. They hire our students. I want to thank them. And I want to thank my 3 current PhD students, Yunqiao Xing, Ojas Kanheri, and Shihao Zhu, who are exhibiting some of the stuff as they kind of follow in the footsteps of George and Shu in trying to tease out the knowledge. Thank you very much.
Well, thank you, Ted, for a very exciting and energetic. This is one of those talks where you almost need a debriefing. You know, because with all due respect, not everything was correct. So, you know, students take your words correct, you know, seriously. One question I have for you is comp. You said, hey, it's not. And we were talking to one of your colleagues, Shiva, I don't think he's here, that, you know, blockage, if you think in terms of latency, right, the other elephant in the room, that's where comp may be useful. Interference is not the issue, but suppose it gets blocked, you may want to use another one.
I didn't mention in the talk, we considered that. We have a blockage model. We have a human blockage model. We published it a year and a half ago. It's a 4-state Markov model, and that was included in the analysis by George McCartney. George actually, and his PhD thesis is open access. He's working on a journal paper. So we considered that. We considered human blockage in the NYU campus layout. And still, even with human blockage, there was not that much outage. And remember, he has all these beams. And the human outage is very slow. You can predict when the person's starting to walk. And so if you have all these beams, you can basically look and quickly make another beam and rescue. We have all that data and showed that you could quickly get away from the blockage and point somewhere else.
Yeah, well, that's, okay. So, you know, it's like, it's not just the physical layer, right? It's the networking layer that has to talk to it as well. Okay, well, any other questions?
Dan has a question back there. That's a great question. Will that still be true at 95 gigahertz? I believe it will be. I think you have some answers in some of your work, but yes, I believe still above 95 gigahertz, you will indeed be able to do the same thing. Look, order of magnitude of 30 gigahertz is 300 gigahertz. Channels don't change that much over an order of magnitude of frequency. In fact, if we used 7-degree beam widths 10 years ago and measured the channels for 3GPP, we would find very similar things than we're finding today. It's just now we know the technology will allow small form factors with very directional antennas. The industry wasn't thinking about that 10 years ago in a cell phone. So yes, I believe it'll follow.
I would, so directionally channels become sparse. I think that's one of the reasons why hybrid works and why interference is not there. And I think so channels do change in that regard, that you're not going to be having this diffuse, rich scattering. That was your Rayleigh curve.
Well, it's a very good observation. He's right that in general it becomes more sparse because diffraction goes away as you get to these higher frequencies. The diffraction is based on the physical world. However, I did measurements as a paper like back in '96 with a giant horn this big at 2 gigahertz, and I found similar sparsity. I published it. No one cared.
That's narrow beams.
Yeah, exactly.
Narrow beams is the thing.
My point is when you go narrow beam at any frequency, the channel by definition is sparse.
My point is that if you go to very high frequencies, any damn antenna is narrow beam.
Yeah, well, yeah, because you have to physically make it.
You can't make it broad.
That's right.
So, okay, well, any other questions before we arm wrestle?
Well, Ted, thank you so much for a very inspiring and informative talk. I have a bit of a technical question. This is related to the clustering model that you have, and specifically to the channel coherence time in a beamforming environment. And just to give you a background, I'm trying to figure out how often one has to do tracking and kind of changing of the beam. So how long does the channel maintain its coherence time under mobility, and how would the clustering phenomenon impact
Great question. Great question. And Shihao Zhu, one of my students, is actually working on this idea of spatial consistency. We have all this data, and we're going to put that model in NYU Sim. We don't have it in yet. The bottom line with coherence time is it's roughly related to the inverse of the Doppler frequency. So basically, what's the Doppler? And when you look at the Doppler at millimeter waves, it goes up by a factor of 10 from where we are in today's cellular. So in a high-speed car today at cellular, you've got Doppler of what, about 200 hertz? So you can imagine up at millimeter waves at a high-speed car, you're going to have Doppler of 2,000 hertz, 2 kilohertz, which is going to be about half of a millisecond. So you basically have 500 microseconds while the channel is static. That's why packet durations of 50 to a couple hundred microseconds will basically be like a static channel. And by the way, that's a very short time, but you can get lots of bits through at very high data rates. So you're kind of looking on the order of fractions of a millisecond while you've got a static channel. And that's a lot of time. The overhead, I mean, we're going to take 5 milliseconds to kind of figure out where all the beams are. You can't go very far in 5 milliseconds on a track. So generally, the channels will be spatially consistent. 3GPP said spatial consistency is within a 15-meter grid. You know what? We made measurements that showed in a 5 by 10-meter grid, the average path loss really doesn't change. So that means the clustering's not changing. So if you figure in a 10-meter distance, whatever speed you're going, the channel's not going to change very much. In fact, we have a VTC paper in the workshop that Kate is heading up. Talks about spatial consistency. So the bottom line is you've got 10 or 15 meters in general, unless you're going around a corner. You know, if you happen to go right around a corner in millimeter wave, you know, you're obviously going to change clustering because you're going to change serving base stations. But generally, you can think that as kind of a stationary region from what we've seen in the measurements. Does that answer your question?
I'll add to that, you know, I think a lot of people, this is another myth that things are moving too fast in millimeter wave, but we have to remember our sampling intervals are in nanoseconds.
Right.
That's large bandwidth, so it's in super slow motion. So you can track the hell out of things. So yeah, that is true. A shorter way of saying it maybe. Oh, yes.
So besides the channel during a packet, right? You say the channel during the packet is constant, and so you can just use it as a static thing. But then when you go to the networking level, it's not just one packet. You may need to retransmit. You may need to schedule and decide when it's good to schedule transmissions. And if you know that your channel is going to be static for 1,000 packets or 1,000 slots, then your ARQ strategy, for example, will be different compared to when you know that every transmission is essentially IID. And so that knowledge, I mean, one can roughly say, oh, at these speeds and at these frequencies, don't worry, everything's going to be static for your signal transmission. But what about, the more complex scenario where you have multiple transmission, you need to schedule, decide when to transmit. And so in that scenario, it becomes important to be able to say what is the correlation in time and in space for a multi-user system. And so I think we need measurements for that.
Yeah.
Right? We need measurement for correlations, because now it becomes important. Now you've done the marginal statistics, right? The PDF of the signal transmission. Now give us the correlations, because we networking people need that.
Yeah, you hear that, Shihao? You hear that? That's your master's thesis. We're doing that right now, actually. He is going through all our database of measurements, looking at the tracked measurements we have, because we've made so many tracked measurements, and he's writing the correlation. Now, we've published correlations on receive fading envelope. In December of 2017, in the IEEE Antennas and Propagation Society special issue on 5G, you will see the correlation distance as a function of antenna of the received power envelope. So you have correlation right now on what's going to happen to the received signal. It's published and it's available. We have the mathematical models. The other thing is the clusters. There's not a lot known, but we're going to get that data. And we've got spatial consistency figured out to a first order, and we're going to put that in NYU SIM so that you can get that correlation over a track.
Debriefing is absolutely in order. So with all due respect, these horn antenna data is not indicative of the phased array narrow beam data that may be used. So we need some more different measurements in addition to processing the old measurements. I know you guys are getting better sounders, and they're going to be built, but
you always need more
degrees,
measurements.
And 20 degrees is too wide. That's not what the systems. We have to measure them at the resolution that they're going to be seeing at the spatial resolution, which is still not being done.
More measurements are always welcome. We're using 7 to 30 degree beam with 72230, but you're right. Look, you need more measurements. So this is so new. The world doesn't yet understand this. And until you measure and see it yourself, you really can't understand it.
Absolutely. Let's thank the speaker again. Thank you very much. All right, we are only 20 minutes behind schedule. That's all right. It was worth it. Thank you, sir.
Thanks, Akbar.
Okay, so readout from the breakout sessions. So we had 3 breakout sessions, and I think what I'm going to do is have you go last, because that's, so the first is Kate. Maybe Kate, you can read out on the hardware, and then where's Marco? Marco is, there he is. Okay, who wants to go? Either Kate or Marco first. So you can come up here, Kate, if you want to talk about it. You wanted your notes. Let me see if I can find the notes.
Test. Okay. Let's see. I don't have my notes with me, but I think Akbar has. Or do you want Marco go first?
While I get her notes?
Sure.
How much time do I have?
We have in total about, let's do, just
Can you just
10
put it
10
somewhere?
minutes, quick summary so that we can be done in about half an hour at most.
10 minutes.
10 minutes
Yeah.
each.
Okay.
So yeah,
I
know
can do
we
it.
can't do 10 minutes.
Yeah, I'll try. I can. I will.
Ted is rubbing on to everyone at NYU.
think he left. I had some comments for him, but yeah, I'm gonna do it offline. I can control from here, honestly. Yeah. Okay. Can you hear me? Yes. Yes. Okay. So yesterday we had the 4th breakout session about signal processing and networking interface. Myself, Tanguy, and Ismail were leading the session. I started off by talking about, by recapturing the goal and motivation behind this breakout being cross-layer open discussion with research communities in the intersection between Phi and Net. And specifically, we tried and challenged and refined the tools and methods used to conduct end-to-end millimeter wave research, focusing on the network simulator NS3 and some ray tracing thoughts. And then we tried to stimulate some discussions about other potential research topics related to this CSP net interface. So I started by talking about something that I created in the last few months after the last workshop. As promised, I created this website, a shared website. It's a Google site where anybody interested can participate and edit and add thoughts and ideas. And as you can see, this is the structure. You have different pages, and we've, based on the 3rd workshop, NSF RCN workshop, we've spotted some topics of interest. As you can see here, we have some MIMO channel characterization, some thoughts about error models and link to system abstraction, and simulation scalability and complexity reduction for channel simulation, millimeter wave channel simulations. We've had 3 WebEx calls offline between these workshops, focusing on these 3 topics with a bunch of people involved. We are 23 participants across industry, academia, NIST, research labs, and so on and so forth. So as you can see, the format is as is indicated here. Every page has its own topic and a hyperlink to a Dropbox page where I upload recordings of the WebEx plus the slides of each presentation. So this is just so you know, and if you're interested, please participate, ask me to access. So related to yesterday's discussions in general, the main topics that were also captured and discussed across the WebEx meetings in the last couple of months are as follow: channel models, ray tracing blockage, antenna partner orientation, hand rotation, Phi abstraction, and simulation scalability. So we started off with a little bit of background on simulating the MIMO millimeter wave channel in NS3, both for 3GPP and R as implemented by NYU, and for IEEE 11AY as implemented by NIST. So this was an overview. Most of you are familiar with this snapshot and this framework. It's the end-to-end millimeter wave module developed at NYU in collaboration with the University of Padua that got recently published in COMST in 2018, where you can find all the details. Then we briefly talked about the channel generation procedures as indicated in 3GPP, which are step-by-step the ways we have in NS3 the channel initialization, the MIMO millimeter wave channel initializations with channel metrics, spatial signatures, complex values, and a lot of complexity indeed. We've also shown that we validated some of the optional features proposed by 3GPP in 38.900, like self-blockage, blockage, spatial consistency. And this is just to show the audience that this is what we have. And we would like, to get feedbacks and people, if interested, to tweak this or just use this because it's an open source tool. And then we've also talked about the synchronization that we've recently integrated, really following line by line the 3GPP guidelines in release 15 with SS burst periodicities and a very detailed OFDM symbol tracking based on that, and also showing that what we can do is not only 3GPP procedures, but also plugging our own measurements, the sounding, and basically get some TCP and higher layer performance evaluations. So this was my first part of the presentation about NS3 millimeter wave channels. Then NIST talked about their very impressive tool developed in MATLAB for the 11AY simulation in NS3 also. I want to stress this because we believe it's the right tool to do a lot of joint works. So they talked about this quasi-deterministic channel model implemented in MATLAB, which will also be released as part of the WLAN toolbox in September this year. And that's being used in conjunction with NS3 to provide this physical layer for simulating end-to-end 11AY, basically. And then Ismail jumped on stage and talked about some of their preliminary measurements with propagation statistics, beamforming, the effect of beam shape on angular spread through their ray tracing tool, and some modeling of blockage and multipath energy in the angular domain in vehicular networks. The second part of the presentation was about abstraction, physical abstraction, and this is where we've got the best insights, and I think there's a lot of space for improvements, joint improvements. As I mentioned earlier, it's key to simplify as much as we can the simulator, the channel part of the simulator, and try and minimize the complexity of the MIMO channel specifically. So I briefly talked about mutual information-based link-to-system abstraction, which is the globally accepted solution to do this sort of abstractions. So I got the audience to better understand what we have there. And specifically, the most important part is this. These are link-level AWGN curves used in LTE for the OFDM evaluation methodology. And what I've openly asked for is help or advice about implementing the new link level defined in NR release 15 to basically rerun these performance curves and refine our error model, because as of today it's based on LTE OFDM at 20 megahertz, and this is even it's just an AWGN channel. But I will recap in the end. So the other part was NIST talking about their error model for 11AY, which is indeed different, and they're working on this, also based on a MATLAB implementation that's part of the 11AD WLAN system toolbox. The last topic we've discussed, so basically just to recap, we've talked about channel, MIMO channel, millimeter wave, both 11AY and 3GPP NR. We've talked about phi abstraction, and then as I stressed earlier, the importance of scalability. We've shown some preliminary results where with one single link, the bottleneck of the complexity is on the higher layers. The TCP and IP takes most of the runtime computation with one link. UDP traffic indeed is easier because you don't have congestion control algorithms. And then what we've shown indeed is if you start and grow the number of base stations and users, the bottleneck becomes the millimeter wave module. Channel metrics, interference computation. So what we've proposed and implemented already is some decoupling for the channel metrics to make it more runtime, but it's still very complex, and it takes long time to simulate multiple users and multiple base stations. So we're working on another technique. We're in collaboration with Nokia. We're discussing with Nokia because they're having very similar ideas. So we might end up doing the same together. They're very open to open sourcing this. It's down selecting some clusters to minimize the computational burden. So this was the third part, and let me now wrap up with this slide where I want you to see what are the next joint steps and a little bit of a call to actions. So link level millimeter wave simulation to improve and refine the phi abstraction for millimeter wave end-to-end and R. Working together if you have ideas about this channel complexity reduction. I think it's an interesting also research topic. We could use technique. Maybe machine learning, but it might be, we've tried and we don't think it's the right way, but if anybody has ideas, we're happy to sit together. Integrating and testing new channel blockage and rotation models, because it's such a modular tool, we can easily plug and play different models and compare. And this was assist to Ted's keynote where he talked about NYU SIM and comp, so maybe we can integrate all that and show the performance, the end-to-end performance differences when you plug these different models. And please reach out to me or to Ismail. I forgot to put their email, sorry, but it's enough to reach out to me for joining in future WebEx sessions that we will have offline between workshops. Just sit in, give ideas, get inspired, do whatever you want. There's a hyperlink here. You'll get the slides so you can click and get to the website. And please know that we would be happy to have you join the NS3 millimeter community, either 11AY or 3GPP-NR. There's a lot of documentations and tutorials. The learning curve is not that steep, and we would be happy to help. Open source is key to acceleration. Thank you.
Thank you. So that's a great summary, Marco, great readout. A couple of questions. So one, and this is going to be really, and I want you to sit in front because you're going to be part of the panel discussion here. So the error rate performance was to actually maybe put it at abstraction of the file layer at that level into your NS3 simulations rather than implementing, that's what the goal of this link error model. Okay, and then file layer right now, is it still single beam in your implementation?
Oh, not at all.
Oh, you don't have? Because
No, it's multiple beams.
You can do multiple beams and multiple channels.
Yeah.
Okay, well.
You can easily plug that in. Right now we're doing, you can easily do multi-user MIMO with the way it's implemented today.
Excellent.
Yeah,
so one question I had asked you last Asilomar, I think, or some 2017, I don't know. Can you estimate latency in your
Of course,
simulation?
yeah.
So what's the shortest latency in reasonable scenarios that you've been able to get?
Oh, so we've shown, it depends on where the server is sitting, right? So when we do edge simulation, where the server is sitting pretty close to the user, we're able to show that thanks to the frame structure and our frame structure and the retransmission procedures, you can easily hit the 1 millisecond.
But that means that everything is on the edge, all the information.
What's that?
All the information is on the edge.
Yeah.
So which the physical distance is maybe hundreds of meters.
Yeah.
So yeah, okay.
So that's pretty easy. And also through handover, because we've implemented this dual connectivity framework where you have sub-6 and millimeter wave. As soon as you lose the millimeter wave link, you can very quickly maintaining the millisecond latency thanks to these lean handover procedures enabled by this framework.
And then you also have the NR standard components in there, it seemed like.
Yeah,
Okay.
highly customizable. Yeah.
Very good. Any other questions for Marco? Okay, let's move on to the next readout. So I have your notes now, Kate.
First, I'll say that I wasn't expecting to do this. Harish was supposed to be here. So we're a little less well organized than the last group with the nice slides. That was really fabulous. And you don't have the Pete's, Harish's, and my slides. Okay. So we had three of us sort of leading the discussion. And I don't have the slides from the three. It was Pete Musburger from Ball. Pete, are you still here? I think he had to leave for the...
I don't know if I have Harish's slides.
Yeah, I think Harish made them at the last second, so...
Okay, so I can get his slides, and then I don't have...
You don't have mine? I sent mine by email to you, yeah.
Okay, so do you want those slides, or you want to just summarize it?
I can just summarize. That's fine. That's fine. Will the slides be on the website, though? I mean, they are...
I will put on the website.
Okay, all right. So Pete is from Ball Aerospace, and so he's in charge of developing their phased array, the 28 gigahertz new commercial sort of prototype that people can use to investigate development of 5G systems. And so he discussed the advantages, and this isn't on the notes here, this is just sort of the preview. Pete discussed the advantages and disadvantages of various phased array implementations, fully digital, hybrid, and more traditional sorts of phased array. And he really made the point that the business case needs to drive the decisions on what technologies to use. So then that the decision on which type of phased array implementation to use may change as technology advances. So for example, people are using hybrid arrays right now. That makes the most sense from a business case point of view, but there may be a time in the future where the fully digital implementation of the phased array starts to make more sense. Harish, he's professor at Columbia, and then he also has a startup called Mixcom, where they're doing RFIC design. He touched on several different open challenges regarding which technology to use for 5G implementations, silicon or 3.5 based or hybrid types of technologies are all candidates right now.
I guess I'm in lag.
So, so this is these are Pete's. These are Pete's slides.
Any more of these? No.
Well, we could step through them. They're just 5 slides, so we might want to.
But I mean, you already talked about it, so let me see if I can find yours.
Okay, okay, and then I'll talk about Harish in the meantime. And then he also talked about which architectures to use to improve system efficiency. So the fact that the amplifiers are need to be operated in very linear operating states right now means the efficiency is very low. That will also probably change in the future, but there are certainly technology or architectures that can improve system efficiency, technologies that can improve system efficiency. And so the choices that are made now are sort of the most safe to get systems up and out the door, but things are likely to improve over the course of the next few years. And we discussed that yesterday here also in the panel. And then being from NIST, I've talked about the role of measurement in improving models.
I don't have your slides, sorry.
Okay.
Did you send me this?
By email, yeah. Okay. Anyways, I discussed the role of measurement in improving models and reducing the need for digital signal processing, things like digital pre-distortion. So I gave a couple of examples on the use of measurement uncertainty to improve the nonlinear models that are being developed for transistor design, showing that if we extract model parameters from large signal measurements, that by doing sensitivity analysis of the various extracted parameters can lead a designer to understand what the weak points are in the transistor model development. So for example, if you run something near compression or high current, you can see very clearly from the uncertainty or error bars that there are weaknesses in certain parts of the waveform as you're nearing compression. I also gave some examples on the use of channel measurements for directional array design. Based on our NIST channel sounder, we can synthesize an omnidirectional radiation pattern. We have a switched array that samples very quickly in the azimuthal plane. From that, we can synthesize an omnidirectional array, and then we can actually take the measured data and start synthesizing narrower and narrower beam widths so that you could, a designer, an antenna designer, could see the effect of various beam widths based on measurements in a specific environment. And then also talked about over-the-air measurements and how those can be used to verify the performance of devices and then to improve the performance of devices. So that's a big issue right now in the 3GPP is the OTA test of the millimeter wave devices because they need to be verified. The performance needs to be verified in sort of these 3D spatial channel models. And so I showed an example of a hybrid chamber that NIST has developed to create specific 3D spatial channel models, essentially in physical space, based on a reverberation chamber that's very heavily loaded with RF absorber on the wall, so essentially like an anechoic chamber, but then certain patches are left reflective to create the angular clusters of multipath that are specified in various channel models. And then the sort of key value added that NIST brings to this is the verification of these environments with the synthetic aperture techniques. So that was sort of the introductory comments that the three of us made. And then we had a very nice discussion, focused a lot on the beamforming arrays, which is not really my expertise, but was certainly the expertise of a lot of folks in the audience. And so the first question that we tackled, will fully digital arrays ever become a reality at millimeter wave frequencies? And as I mentioned, well, there's a lot of advantages to fully digital, so people are trying to head that way. The hybrid array is not as efficient in shaping the beam, but the hybrid array, I think this is the big advantage right now, only uses a few ADCs, and then of course, one RF or fewer RF chains as well. So, eventually, I guess right now, and Ted touched on this also, if the millimeter wave use case is primarily line of sight and maybe has 3 or 4 clusters, does it really make sense to use a fully digital array, or are we fine with just a hybrid array having 4 or 8 various beams that it can create? So that's sort of a fundamental question. Fully digital is quicker when it's used for the initial access, the discovery of the channel. So, ultimately there are probably advantages to using that. It may be, this is something Pete brought up, a fully digital system would likely be more difficult and complex to maintain in the long run, just because you have more of these moving parts, the active parts, the antennas, or sorry, the RF chains and the ADCs. Let's see, and then there was a discussion on this concept of open loop beamforming, where you don't monitor channel conditions in real time. You just assume that the coupling between the elements is constant and that you have adequately tuned your array for, to minimize blind spots. Closed loop beamforming, you can compensate for non-idealities like coupling and unexpected scattering in real time, but at the expense of power. So power is a big issue for the millimeter wave systems and the system complexity in terms of the long-term, maintenance and usability of the system. So it was argued that open loop is generally satisfactory, and if a few elements are operating in a nonlinear state, like because of coupling, signal conditions, or something like this, it won't be all of them. And so, and that tracking and blind spots don't change that rapidly in practice, so that gets to this idea of the coherence time of the channel, and that we're really mainly tracking 3 or 4 clusters at a time. So let's see, for now the cost of a fully digital array might be high and the reliability might be low, but that's today. So the potential is very high for using fully digital arrays if lower cost ADCs could be produced as technology advances. And so there was a lot of confidence in the room, I would say, that fully digital will be a reality at some point. I mean, everyone pointed out that right now in the sub-6 region, we have fully digital arrays, and 10 years ago, you never would have thought that could be possible. So one of the questions that Harish brought up is, but will 5G, is 5G a large enough business or commercial entity to drive the development of these low-cost ADCs? And so perhaps other applications might drive the development. For example, if Internet of Things really takes off and in the industrial environment or these other very high reliability use cases like automotive applications, perhaps the millions and millions of nodes that would be a more likely driver for the development of fully digital arrays. Let's see. If the applications are primarily line of sight, why use beamforming at all? These are questions that came from the audience. Why not use mechanical systems? And the answer there is that right now, it's performance versus cost. So operators do not want this first generation of 5G to fail. Phased arrays are proven. We know that they can work in this hybrid technology. They're cost effective. So that's what is going to be used right now. Let's see. Acquiring channel state information. Is there a high overhead for training fully digital arrays? In mobile multi-user applications, fully digital is more powerful, and I think Sandeep had a paper to demonstrate that. To make digital arrays more cost-effective, you could reduce ADC resolution. Okay. All right, on to question 2, augmented virtual reality. And this was just interesting. It was estimated that each user would need 3 gigabits per second of data with a latency of 10 milliseconds or less. So can 5G do this? Well, the panel sort of said, well, maybe 6G. That really is beyond the capabilities of even current, in the near future projected technology. Question 3 on PAs, power amplifiers, and digital pre-distortion. For example, if you had 256 power amplifiers in your array, and not all of them compress at the same time, how would you apply digital pre-distortion? Can you use an average over the entire array? Well, you could actually apply digital pre-distortion on each data stream. So again, if you had a hybrid array, you would be applying the pre-distortion on each of those subarrays individually. So that's maybe not a showstopper. There was also some interesting comments on third-order intermodulation products. If each power amplifier in an array creates its own intermodulation distortion, and the IM3 has a different phase from that of the main beam, it essentially creates its own distortion beam in some undesired, maybe not random, but undesired direction. So various research groups, and I thought this was really interesting, are using shaping techniques to direct the distortion products, so the beams that are caused by the third-order intermodulation distortion away from the desired directions. You could also direct, and then Harish brought up the point that, well, maybe using these techniques, you could actually direct IM3 away from a receiver in the presence of a blocker to overcome some interference issues. So these are just ideas that came out of the group. And then the final question was, the new radio bands are very reconfigurable. LTE always had a fixed, you designed your system to operate at a fixed 20 megahertz bandwidth, whether you use the whole 20 megahertz or not. That was the system that you designed. So what are some of the issues in hardware circuit design for systems that are very reconfigurable? And this answer is very abbreviated, but the bottom line here is that reconfiguring hardware, so components like filters, and then the ADCs with the sampling rates, it's difficult, but that there is quite a bit of research in the area. So that's what we had. Any questions? Or?
Yeah, let's see. Is there another mic or is it over there? Any questions for the hardware breakout? Well, one thing I was wondering, so in terms of the interface signal processing, it seems like pre-distortion techniques, clearly signal processing, has a role to play in terms of the subarrays. And then in the filters, some of this, why do we have to have hardware reconfigurable filters? You could do it in software too, that you're only using sending signals on a partial stream. It won't be as, the leakage won't be as controlled. So I don't know if it's necessary or not.
I think that the trade-offs are the power consumption and the complexity that's required to implement things in signal processing or DSP versus hardware itself. And we actually talked about some groups are trying to get away from the use of digital predistortion and go back to sort of the old techniques of using analog circuit design to compensate for distortion. This idea of coming up with better designs, maybe using lookup tables more as opposed to real-time analysis. Any little tricks that companies can use to minimize power consumption, they're really trying to do that right now. And so I think hardware implementations are actually more, are less power hungry typically.
Power hungry, yes. Yeah, I think that's a good point. Okay, that's one of the reasons why hybrid beamforming is being used as well. Okay, any other questions for the hardware signal processing breakout discussion? There'll be more of it, so thank you, Kate, and please, you should sit in front too so that we can ping you. And so the third one was on testbed development, and we had a very sparse session because everyone else was elsewhere. But it was the most important session. No, I'm just kidding. But this was about, and I think some of the themes that we would really like to discuss here in the panel discussion following too, in addition to some of the big problems. That one is research testbeds for the academic research community. So one of the consistent things that has come through all of RCN meetings is that, hey, it's very expensive, time-consuming to build these test beds. And so I think one of the things that we're trying to see is there's been activity in small pockets, and we want to see, is there a will and need and desire by the community to actually create a community-wide test bed where different people, like hardware folks, can develop their hardware, and then FPGA folks can develop those algorithms there, and maybe ADCs, and more modular, so that we can have end-to-end performance assessment and less structured, less constricted than what are commercially available right now, and then it could lead to the power platforms feed into those as well. So I'll let Manu talk about.
Perfect. Thanks, Akbar. So this was a session, and if you wouldn't mind just raising your hand. So the participants were Greg from BWRC, and Hang from Catholic University, and Kira out there in the back from National Instruments. And myself, I'm Manu Gosain from Northeastern University, and the hat I wear here is as a member of the Power Project Office. So essentially the motivation here was to answer some questions. Again, thanks for the introduction. So we didn't really do presentations. We actually really wanted this to be hands-on and address some fundamental questions, since at least in my, this is my first RCN, but having looked at previous agendas from the previous workshops, this is the first time I think a community testbed session was addressed. So we sort of wanted to level set first with the members, with the panelists, as well as the attendees, what exactly the state of millimeter wave research testbeds is, at least in the US academic community. And essentially the first testbed of its sort that has been funded by the National Science Foundation under the umbrella of the PAWR Platforms for Advanced Wireless Research Program is the Cosmos platform. And yours truly, NYU Wireless, is a member of the team. So is Columbia University, so is Rutgers University, and so is the City of New York. And the goal is to basically deploy a citywide large-scale wireless testbed and end-to-end system. So as you can see, millimeter wave is just the RF enabling technology, And not only that, it basically, given the cost trade-off, will effectively be only available on about 25% of the deployed sites around the Columbia University campus. So we are actually looking at field deployable millimeter wave systems at 28 and 60 gigahertz. And essentially, one of the first comments that came from the group is that's what 5G is doing today. We really want to push the envelope and look at spectrum horizons above 100 gigahertz. So what can you do for us? And the answer was nothing much at this point, at least in the power context. So that was a good input to take in for the testbed community to develop something that does not exist today, or maybe exists in small pockets and only for a very few subset of people. So that was sort of the power story. That's essentially the only NSF-related academic large-scale community, the emphasis being on community, meaning it's going to be available to all the researchers here in the room, as well as the broader research community. After that, Greg briefly talked about Hydra, which is being built or has been built at the Berkeley Wireless Research Center. And essentially, I don't want to butcher the details, but it's a massive MIMO 75 gigahertz, 128 element millimeter wave system. Currently works only in the uplink side, so they have about 60 clients and the base station, and they have a working implementation on the uplink side, with emphasis being working on getting the downlink going, because that's how you discuss or research on higher layers, network and MAC, etc. So then we sort of tried to answer or tried to discuss some of the fundamental questions of how does a testbed benefit this community? And that's when we started to narrow in and focus mostly on meeting the needs of this community, really digging deep into the physical layer specifications, layer 2, layer 3, and not as much worrying about applications and transport at this point, because we need the base infrastructure here, and we need some consensus in the community on what's important and what needs to be done. Again, for the US academics in the room, there are some instruments available in the National Science Foundation funding cycles, specifically CRI and MRI, which are used to award infrastructure grants. So the goal here was where do we stand in addressing the fundamental research challenges in millimeter waves, and at what scale should we be imagining or envisioning specifically building millimeter wave systems and testbeds? Are we at a point where a community scale or a community size, large scale, shared testbed resource, are we at that point, or are we still at the point where we need instruments which you basically can get funded through small MRI grants and basically represent or develop channel models? Obviously, we heard from the keynote that more measurements are always welcome, but have we sort of gathered enough data and come to some consensus that we want to take the next step and actually develop something as a community that's going to be useful to everybody? Question 3 was something we did not get to, but again, just to put it out here in front of the audience, the goal here was to actually understand who the actors or what the terminology used for this testbed would be. So to reflect this back at the group, essentially looking for volunteers in this community who would want to be either a experimenter, meaning a user of the testbed, a testbed provider, so a person or an institution that's going to host this testbed or the system, or actually develop it. And then the third, and quote-unquote the most boring part, which is actually keeping the millimeter wave testbed system up and running. So these are sort of the candidate roles, and again, we're looking for members in this community who sort of raised their hand, and we did get some volunteers for a couple of those options there. Fourth was sort of to level set, I think something that was said on yesterday during the industry panel, which is essentially from companies and industry to stay away from the modem and the silica. So as the closer you are to the device end, the barriers to entry are very high. And essentially, that's something that us as a community trying to get access to millimeter wave systems will have a very hard time. So we need some partnerships. And there were some creative solutions that came up, and I'll get into those. And I think that's sort of one of our most concrete steps that came out of our discussion. The cost performance trade-off models. So essentially, I think this again is to justify the cost and the investment needed to build these community size or individual campus size test beds. As you can imagine, currently the state-of-the-art or commercially available solutions sort of are quite pricey, and again, you need to be part of either a very prominent research group or a research center to even get access to some of these instruments. And the goal here is to sort of somehow democratize that access by developing these millimeter wave test beds. The other one, so the next point was essentially an action item of sorts, was to conduct sort of a gap analysis, paint a picture of what's actually currently available in terms of systems, both commercial, open source, some academic efforts such as Hydra and the Power Cosmos platform, and basically try to understand where the gaps are and where actually this community can develop, and where we actually will need to partner with some industry members, and how do we entice them, or how do we put a value proposition to actually attract industry to contribute to the test bed. A couple other things just brought up more for information's sake was looking at other open source communities, specifically in the telecom space, the Telecom Infra project. There is a Telegraph 60 gigahertz point-to-point radio developed by Facebook, which they now have opened up in what they're calling a sounder-in-a-box program, where as an academic, you can actually go and apply to obtain one of these radios and actually use them for channel sounding in 60 gigahertz if needed. So that was more informational here. I did share a slide deck with Akbar, and please feel free to post that to the website. Then we got into, what sort of experiments could a testbed support? I think this sort of was relayed back from the comment again made in the industry session, where in the standards bodies, there was people who work on radio and people who work on network aren't really talking to each other. So that was another motivator to build an end-to-end system, a millimeter wave system, where actually these different silos are forced to talk to each other and come up with standardized or common APIs or common interfaces between layer 1, layer 2, layer 2, layer 3, which currently, at least in our understanding, do not exist today. So that would be another work item that can be taken up here. Last but not the least, a big thing was, if these systems are being built, they need to be highly calibrated, they need to be really well managed, and the data needs to be very clean, well managed, well documented, lots of metadata, so that any of the data, either IQ samples, channel state information, whatever is captured, is useful to the users of this eventual testbed. I'll pause here if any of the panelists want to jump in, if I forgot to cover any item. If not, I'll move on to sort of what the, do you want to add anything, Hang? Or, no, okay. So basically what came out. So some of the action items that came out, I think the biggest one that came out, and I think garnered a lot of excitement, at least after the session, where some other volunteers from other breakout rooms came in and sort of jumped in, were to actually build a reference design in this community by building together or piecing together all the different research done at the system level, some at University of Wisconsin-Madison, some at Berkeley, and some at Washington State University. The idea being to have a very modular approach to pick out all the discrete components and actually do a layout, an RF board layout, and essentially spit out something that can be developed or something that can be shared with the broader community, where the community can raise their hands and say, yeah, if you build this, I'm going to use it. And essentially what this gives us is the collective bargaining power to go out to a manufacturer or an RF assembly shop like QuickPack, et cetera, to actually build these things, and also gives confidence to the federal agencies such as NSF to see that there's community interest in a project or in a system that's actually been built from the ground up, completely open source, at a price point or at a cost that can be afforded and can be distributed at a wide enough scale. And that was sort of, I think, the big one. Again, I'll pause here, wait, if Greg or any of you want to add anything or fill in the gaps here. Any questions from the audience about that approach going forward? Because one of our goals, at least on the session, was to think about the next couple of RCNs, that there is a year and a half left. So the goal would be to output something, before the next RCN, at least gather things maybe similar to what Marco has done in a shared Google site and start contributing some of these discrete components if you have them available, or point the broader group to who you've been working with on your supplier side if you've been building these systems, and sort of come to a consensus so we can present back to the community the next time we meet as a group, with a broader goal being in a year and a half coming up with a concrete proposal that can be built or written into a grant proposal that can go and be received by the NSF under the purview of any of the programs that were mentioned earlier. In addition to that, the idea here is also about the other large-scale efforts that have been developed. So I mentioned the PAWR program. The timeline for that project is to deploy their millimeter wave system. So I apologize, I think I skimmed over the details, but essentially the phased array system that the Cosmos platform's using, and again, Sandeep and Harish are part of that team, is an IBM Ericsson 64 antenna element, 28 gigahertz phased array, which has 4 ICs. So it might not be it might not be useful for some of the really tackling the fundamental research questions about, so there were points asked about, will you get per antenna channel state information? Maybe, maybe not. I don't know, Sandeep, if you have that information. Yeah, if you oh, there's a mic there. If you want to add, so that was a question asked about per antenna CSI from the IBM phased array.
Right now, it's a phased array, so you can only get that to the extent that you can sweep over with multiple phases. I don't know if that was your question. So it's an analog phased array. So there's 8 anyway. I can give more of the details, but it's not digital on each one.
Well, yeah. So. I think you're raising many interesting and good questions, but I'm still seeking some answers in terms of, for this community, to take advantage of power, and specifically Cosmos Power. I know this is just has started. Those of us who are not directly as part of the two teams, how are we, what's the mechanism for getting involved? And maybe relatedly, and this is more like to NSF and the power, I know there's an upcoming phase supposedly intended for the research efforts to make use of the testbed. What's the timeline on that part?
Can I add, what about non-US institutions?
So that one I'm going to beautifully just deflect, and that's my karate move right there, goes to NSF. I unfortunately don't have the either authority or anything to talk about access per se. What we have done is talk about federation with European testbeds and platforms similar to the 5G efforts that are coming up. So 5G in Fire, 5G Tonic, all the testbeds that are coming up. We've started discussions. I think there is an open call in the EU ICT 21 that's going to fund CSA, a coordinating entity that will essentially interface or liaison with the PAWR program. So I think that's going to be a venue where that question actually gets addressed on what the mechanics are for access, what the federation, identity management, all those thorny issues that need to be sorted out. So as I said, I'll deflect that piece, but for sure that's on our radar. With respect to when is it going to be ready for the current community? For the Cosmos platform, again, Sandeep can jump in any time, but in fall of 2000, so when the Cosmos team submitted their proposal, they submitted a large number of sample representative experiments. Some of them were based on millimeter wave. The early ones are going to be done by the NYU and Columbia team, as well as they've solicited some lead users, extreme users, quote unquote, to actually provide feedback on what these systems are capable of doing. So questions like, CSI per antenna on millimeter wave systems. Okay, if you can't give us, what can you give us? Is it useful enough for us? So there are a series of workshops starting in fall 2018, which will sort of recruit users in each of the domains that Cosmos is building. So there is a millimeter wave component on the RF side. There's a fully optical, reconfigurable optical backbone overlay, which will basically address that community. There's a networking SDN edge cloud component. So these components will run multiple different workshops to gather user requirements input, as well as develop sample representative experiments that will be available to the broader community. In terms of the go live date for the platforms, when it will be available, in terms of what the development roadmap or timeline has, that has it for late November 2019. So that's a year and 3 months, from now, is when it's open to everybody. Because it's effectively, if you think about it, it's not just, it's an infrastructure project. It's essentially building a city-scale network. So we're sort of some of the issues that Ted laid out at the end about right-of-ways, access to streetlight furniture. We are going through all of that.
All right,
I mean, the team is too.
So yeah, I think I would like to make a few comments about that too.
Sure.
That so we are getting, and I'm sure that this is hello, that this is a confusion. People are getting power. So this just one of the discussions. There are two different things going on. We don't want to make this a power session. They just started. I'm sure NYU and Rutgers and Columbia would be doing their thing. That's going to be happening. But the test bed, a lot of people have this misconception. What is power doing and what the community test beds that we were trying to get an input on, that the first bullet item that Manu had. So I want to just clarify a couple of things. Power, all of these power test beds are going to be more infrastructure, and all of them should be able to support millimeter wave experiments. Cosmos is one where that is one of the components of it specifically. The later ones may have bigger components on that. But what we are looking at, one of the things that in this panel discussion, and I want to just make some brief comments, is maybe towards the second half, we will discuss it more explicitly, is what is the need? So some people may be satisfied with, working with power platform, whatever they provide them. But there are other people, I would say my group at Wisconsin, we were building, and I have to be careful, we are building a test bed, and that's going to be, we have a different, less expensive way of doing beamforming. We're also trying to create an end-to-end solution where we built all the RF hardware ourselves, antennas. We have FPGAs too. We are developing the code. Berkeley is doing that with Hydra. And so, some places are trying to get that end-to-end system, but different people have different expertise. There are other members of the community who are not here today who are taking 60 gigahertz thing, velocity or something, and they're more focused on network layer experiments and end-to-end. So the goal here is there an interest in the community to develop something in parallel to power, or almost independent of power in some ways, which will enable smaller scale experimentation within their institutions. So one of the ideas which Greg came on, so first thing would be, okay, who are the RF people who build antennas, who are interested in building antennas for the such test beds, or RF front end, for example? Who are the people who would be interested in ADCs, DACs, and looking at those boards and combining that with FPGA backends, because you'll need FPGAs for any kind of real-time implementation? And then who would be interested in developing the FPGA code so that you can even do or interface with an end-to-end networking interface? These are different expertise, but I know that in this community, all of those folks exist, expertise exists. And then, so first thing is identifying who wants to work on these modules, create community-wide specifications for, what are the needs that we need, modular, and what it can do, and then fill in some of the other expertise outside ones where, for example, these RF boards will be integrated, so, we have to outsource it to some companies. We don't have to work with big companies, and we are not, this is not a commercialization pathway, so we're not intruding on any big companies or anything. So is there an interest? Who are the players who would want to actually do the work? And then who are the researchers who would be interested in getting access to that platform, and at what cost, so that we have a complete idea of, okay, this is what we need, the community agrees to that, and these are the people who would build it, but at the end, once it's ready, perhaps there'll be 50 institutions who would be saying, oh yeah, we'd be interested in replicating that system at our institution. And so we need the community to kind of develop that roadmap if there is an interest, and we'll come back to that, and we'll send emails about that too, and then create a roadmap, plan, proposal, blueprint for what to be done, and then what resources are needed, and see and then, present it to us, and we'll see if we can make it happen. And now this would be complementary to Power and any other platform. It could be, I can see it being in Utah. I mean, it's a beautiful place for doing experiments. And New York City, absolutely. So it could be put in any and all Power platforms. And yes, international collaboration, I think there are many, many multiple dimensions to it. And but I think I'm not fully prepared to answer that question right now. But it's, yeah. For what? This second thing? The second part I'm talking about? Yes, yes. So what I'm saying is that right now, the CRI, MRIs, people can build components. So we can leverage those, or there could be new programs too. It's a question of, NSF wants to listen to the community. What are their needs? That's our Power program came around, right? So what are the needs? If really there is a need the community feels, and I've heard that, but are there people who are really interested in actually doing the work and working together to do it, then create a plan which is compelling, which you believe in, and then let us do the rest of the job. We will try our best. So anything is possible. Okay, so I'm going to stop there, and now let's get the second panel. Where's Sandeep? Sandeep had some questions. We only have 2 official panelists. Please come on over, Ozge and Zoe. Yes, yeah. What is the deal?
Sorry, it's so cold. But, no, I'm good. So we only have 2 panelists today, but so hopefully the rest of you will just pitch in and we'll make just a free floating discussion. My own contributions here are just to stimulate this a little bit. Okay, so how much time do we have?
That's exactly what I was going to say. It's 10:20 right now. We have until noon. And so what I would suggest is that we kind of, you have some slides, so we go maybe up to 11:15 on the first part, and then between around 11:15, we loop back to this community discussion to see if who are the people who are interested? How many people would like to have more of a community testbed discussion parallel to Power that I talked about? Or how many people are building something along those lines that they're at your institutions? Where are you from?
I'm from Internet Works.
From where?
Internet Works.
Okay. Yeah. Very good. So there's some other, okay. Above 100 gigahertz, absolutely. Okay, so yeah, so I think let's say 11:15 or so, and then we loop back.
Yeah, in fact, you have to leave, yeah, so. Okay, yeah, okay. All right, and, okay, so, Ozge, if you were around yesterday from Qualcomm, I'll just skip the introductions, and Michaela Zorsi from the University of Padua on the networking side, which is, had a little less discussion in this RCN, so hopefully we'll talk about this. So I just wanted to, let's just to start off the discussion, talking about moonshots is really talking about requirements, and this famous graph, which has been reproduced in different ways, was from the IMT 2020 vision, I guess was set now maybe about 10 years ago. And I just want to start up, and it sort of put 3 types of requirements, either in terms of throughput, latency, and connectivity in terms of number of devices, the latter one being related to energy requirements. My view from looking at this right now is that all these dimensions are pretty much technically feasible. The prototypes that are being done are pretty much meeting them right now, but it's a question, I think, of getting it down to cost and getting the coverage out. And maybe just to start either with our panelist or anyone else, where are we in terms of that, and also maybe what would be reasonable targets for what's next in terms of these phases parts. So Özge or Michaela.
Yeah, I think in the last couple of years, we've really just focused on one aspect of this, just the mmBB. And that's just the industry's been focused on that, especially on the millimeter wave side. And I mean, specifically on millimeter wave, mmBB was the clear target. And it's hard to imagine, what kind of a role it would have in, ultra low, high reliability, low latency part is fine, but the reliability part, there seems to be a place for it in industrial IoT. If we can get the cost down, but really it has just been mmBB. And on the mmBB front, if we had this conversation maybe 2 years ago, it probably didn't seem like it was that cost effective. It wasn't that clear, but now it's shown to be cost effective. Once the industry puts all the resources to it, it becomes cost effective. So I think
So you think it's just once it scales to the right volumes, you don't foresee there being a cost issue with building these devices?
Yeah,
at least on the smartphone side.
I foresee it. Yeah.
Michaela, do you want to just quickly talk about on the networking, on the low latency part? Where are we now?
Yeah, well, I guess I wanted to make a comment that I think we've seen a lot of focus on the high rates, the millimeter wave, closing the link at these frequencies, showing that this is good and this works. I actually think we don't have a good understanding of how the network will work. I don't think there is enough work done. And, in a way, I'm a little uncomfortable with this focus on test beds, because I think we also need fundamentals. We need fundamental understanding. Being an academic, I'm all for that part, mostly. And I think the fundamental trade-offs that are there, I don't think they have been explored sufficiently. I wouldn't even be able to say if those trade-offs are just the same as we know from other networks, just with different parameters, or there is something fundamentally different. Coming from the networking side, just an example, the need for directionality. Ted made the point that directionality will solve the issue of the path loss, right? Because the antenna gain will compensate for the path loss. But then, when you look at it from a networking perspective, there is a delay issue, which is there. There is a mismatch between coverage in the data plane and the control plane, which will make these networks harder to manage. And so all these trade-offs, people are looking at the extreme broadband, the ultra-low latency, the energy issue, the coverage issue, but are we looking at these together as a multidimensional space where we need to find the good operating point or the good trade-offs, so the boundaries where we can or cannot go? All of this, I think, hasn't been done in this community. There are some people working on networks, and there are some contributions there, but I think much more is needed. And so we're happy with all this physical layer work and link budget and measurements, but really we need to go to the next level and show that these networks can work, can be managed. It's hard because experimentally you can't do much. Simulation-wise, you can do more, but we discussed yesterday in the breakout group, simulation has its own limitations, so that's another modeling issue that needs to be solved. So, if I look at it from a network perspective, nothing has been completely solved yet. And so I don't think it's a moonshot, because, we're talking about the system we've been looking at for many years. But really, I don't think the progress in the networking area has been as significant as it should have been. And so I see that as a wide open area where we should really invest a lot of brain power, and also looking at fundamentals, analytical tools, maybe some simplified models that get insights to be complemented by these measurement and experimental platforms, certainly. But as a mostly academic community, I think we should try to provide what we are best in, right? Which is, insight and understanding.
It's interesting. Maybe one way to think of moonshot is, what would be the ultimate theorem that, like, if you think of, okay, like MIMO had the capacity formula, there's a single, expression that encapsulates the whole MIMO theory that was really revolutionary. And there are similar results in queuing theory and in network and TCP, but there's been really, maybe I'm wrong, but I don't think there's been a single or really significant theoretical result of that nature.
Some information theory approach where you include explicitly this flakiness of the channel, these extreme dynamics, or this inherent diversity you need to have, multi-connectivity and all that. Does that change fundamentally some of the theorems we know? Some of the, the Shannon type, maybe, but we don't really know. We haven't thought enough about that.
Okay.
And if I may add, let me see, on the
testbeds are, so I'm going to, you're saying, right, that, hey, we need to do fundamentals, so I agree with you. And what I'm getting at is that, we don't necessarily know, as you said, what is different here. So I think there's something very different here in terms of the characteristics that achieving this latency, low latency, is going to be challenging. And there's a lot of things in the air. And testbeds, the hope is that, or the goal is that we actually build these testbeds so that we can answer those questions in parallel, so that, you can have a theorem which may be irrelevant, right? Because it makes assumptions and you have a beautiful theorem, but it's useless. On the other hand, you could have a testbed which is useless too, because it doesn't allow you to answer meaningful questions. So it's somewhere in the middle. We want to join forces. Can't be this or the other. And industry, with all due respect to industry is going to go where they are going, right, where they can make the most money. And so they'll give one straitjacket after the other, which is not going to let us answer the fundamental questions necessarily, because they'll have a specific way of doing things which are cost effective at that time. So that's the goal here.
Okay. Wait, sorry, how much time do we have here right now?
45 minutes.
Oh, we have 45 minutes total. Okay, tons of time. 45 minutes. Okay. So on that note, one way to think about, I put this up because, is it too early to be talking about, how would we want to change? So that, for example, there's this 100 megabit per second number on the mmB, or the less than 1 millisecond latency. And I guess in different parts we've reached or not reached these. Is it too early to be thinking about what would be the numbers as a moonshot to go increase these? Or is this even the right way to be thinking about what is a moonshot, or the next step, at least, for the field?
Well, is it all about numbers?
I don't know. That's my
if,
question.
If this is about improving those numbers by an order of magnitude, we can agree that's a legitimate goal, or maybe it's not a legitimate goal. Maybe there's something different. I can certainly see increasing the data rate as something we may think of. Now, decreasing latency, I think you're going to hit some physics, because there's only so much distance you can cover with a small latency, and so at some point you're going to hit that. And so you either decide everything's going to be heavily decentralized, or you're just giving up, because that's not going to happen, right?
All right. The other. Oh, go ahead.
Yeah, I think that, so the data rate part, we can always increase it by just, right now we're talking 5 gigabit per second for a UE, but then you can always add more layer if you densify enough, and you can go up to 256 QAM or further, or do channel bonding across 28, 39. You can always increase it, but I think the fundamental issues will really just be trying to make this more robust and more stable. And because when you come to data rate, even 5 gigabit per second, everyone loves it for a PR, and everyone will put in the headline. But when you talk to any operator, they don't know what it's going to be used for. Right. They'll admit that there's no need for it until someone comes up with an application that requires it. So then they just throw VR there, because VR is the only application that is in the gigabit per second. But then, is there really a business case for VR in a public environment? Where are people going to walk around with a VR headset? I doubt that. So right now, I think the main focus really should be the stability and the lowering the power and making this more cost effective before we start increasing data rates.
So what is, I mean, also put up here, so we've seen that, you know, in a lab situation with kind of infinite resources, you can create these high data rates. And we mentioned, you're saying that the economies of scale will drive down the subscriber cost. But if we look at the network side, what's the, you know, cost barrier to delivering, you know, even in the order of, say, 1,000 megabits per second throughput universally? Is that affordable right now from the operator's side to put in the network equipment? And what would it take in terms of research to get it, or development to get it those cost factors down?
Yeah, I think the small cells themselves have a cost issue, and it's really on the RF side. So there's really no cost-effective phased array right now for macro small cell stations, and that's where I think the you know, leveraging the UE side will help out quite a bit. So any development on the UE side where you're deploying millions of these devices, and if you can leverage that on the base station side, and that's going to be key. Then there's also the deployment part of it, of course, of trying to bring backhaul to all these small cells, because yeah, you really have to densify enough so that you do have a robust deployment. And if you densify, then you have to run fiber or a wireless backhaul. But then there really is no appealing technology right now that, you know, unless you go for the proprietary technology that allows you to get the wireless backhaul. So that's why I think the integrated access backhaul work is quite important to really have a cost-effective deployment.
Yeah. Another thing I was thinking is from network side, this protocol overhead, right? So, you know, this 4G or 3G or 5G protocol stack, if you take a look, is very complex, especially this control signaling or PDCP, all these things. And also some of them inherited from this legacy phone network. So it's, from network side, I don't know, for the 3GPP point of view, is that their roadmap, you know, to all this GDP tunneling, all these things. So is there a way to simplify it, you know, and make it, you know, I guess they are trying to get more flat network, you know, but so is there something to reduce this overhead, because this is related to the latency and also the cost, right? So from capacity point of view, you can always, you know, and change, improve the physical layer, increase the capacity, you know, and even you have some control overhead, probably you can compensate that. But from latency point of view, probably is more important, you know, and to take a look at the stack, you know, to see where we can simplify it to speed up the process.
Yeah, there are actually several dimensions to this. One is the device complexity, right? If you need to run a complex protocol, then you may need more resources, and on a cheap IoT node, you may want to relieve that complexity. So that's one thing. The latency, and I would add energy as well, dimension when you have these complex protocol stacks. This has been addressed. Clearly, it's a known problem for IoT, right? Because you send only a small piece of data, you have to exchange, you know, 20 times more messages in order to do that. So that's a problem which is being addressed. I'm directly aware of some work coming from Aalborg University on simplifying LTE for this, you know, machine-to-machine type, where they try to compress these handshakes, this exchange, you know, back and forth of signaling messages by maybe combining functionality into the same message. So this is being addressed. And so, but that's clearly, you know, one way where we should go, especially in this machine-to-machine or IoT type of scenario. Now, another issue related to this, I would say, is about the network architecture, right? So not just the protocol, but the network architecture. So what is the network architecture going to be? And you know, we face a lot of complexity in terms of heterogeneous nodes and traffic. We face a lot of issues about, at least in millimeter wave, for multi-connectivity, and so, you know, this comp type or maybe, you know, quick handover or multiple connection active at the same time type of issue. And even though 5G, suggests an evolution of a cellular systems to a new cellular system, so does this have to be cellular? I mean, people are talking about, no cells. Would that, actually a question, if you do away with cells, right, whatever that means, is that simplifying the network architecture, or would that complicate the network management? Right.
So,
yeah, here's that's fair.
Parmesh Ramanathan from University of Wisconsin-Madison. So I'm not quite answering the thing, but yeah, part of it is like, if you're thinking of the moonshot, I think some of those things have to be on the table, right? Including whether we want to get rid of IP. I mean, I know various times over the years I've been in this thing for 30 years, and we have predicted the death knell of TCP or IP and those kinds of things. But we have never ever got there. But maybe this is the time for us to think through and make some fundamental changes to the networking stack, because it may not be feasible to get those low latencies, however lightweight we go. I mean, we have been working on those kinds of things for a long time, how to make it lightweight. And it's just not feasible. I mean, or we have not had any good breakthroughs on that thing, and that's why we are stuck with TCP and IP, right? So maybe we need a completely different network protocol stack completely.
Maybe just on the complexity issue. So the 3GPP, of course, has, in one sense, simplified it because they have the data plane separate from the component. That was already a case in 4G, and they partitioned it even more in 5G. And in terms of the network architecture, they've made it extremely configurable. So you can have the kind of standard, more centralized packet gateway structure, but also distributed gateway structures. And then with the network slicing and network functional virtualization in 5G, it's extremely configurable. But I guess there's two issues. We don't really know how this is all going to be used. It's almost like it's even worse than the Airlink, which has a million different options. In the network, there'll be even more. And the other part there's another type of complexity, which is just this, if you try to, we're going to probably hit this when we talk about the testbed development. If you actually there's a huge barrier to entry to implementing these protocols, even if theoretically when they're implemented, they're extremely fast. I mean, there's just thousands of pages of specs and aspects of these protocols, and that's another type of software complexity, which it's another whole issue. Maybe I transition. We can come back to these, or at least in the context of some use cases that might drive what we think about. Moonshots. So if you look at, of course, there's a standard for everything in 3GPP. So if you look at 38.913, when they were envisioning for 5G, they list a number of use cases. Hotspots, connected cars, highways, all sorts of things. So I just want to go through a couple of these and wonder, how close we are to these, and whether any of these might define how we're going to direct research. So let's start off one that's come up in a lot of discussions about connected cars. So connected cars is, of course, connected to autonomous driving. Where are we now in this? And how is this driving 5G, and how will this drive requirements? And maybe instead of going to the panelists, I'm going to flip this over to Tomi, because I know he gave a talk about this at IEEE 5G Forum, and maybe he can. I'm sorry to put you on the spot there, but you're sort of knowledgeable in the area.
Yes.
And you just introduce yourself.
Okay, Tom Svensson, Chalmers. So the question was, where are we today in connected cars?
Yeah, that's right. And how is this going to drive the use cases for 5G, and what we should be doing in terms of wireless research in the next 5-10 years?
Yes, I think that there are different perspectives, different parts of the world, and academia, and telecom industry, and automotive industry, and inside the automotive industry there are also different views. But I see a moving trend towards connectivity of vehicles in the automotive players, away from ITS, DR, SRC kind of connectivity towards network assisted. They start to see the value of it. So I personally, I think that there will be steps. They will start with the SRC kind of connectivity, to implement the basic ITS services, And then every vehicle will need cloud connectivity, and that will be more and more data. And when you have these modems, they will start to see the added value to harvest what I normally talk about, improved information horizons, because that's what the mobile network can add to the control systems for active safety assisted vehicles and towards fully autonomous. So we have a EU project called 5G Car in Europe.
What's it called?
5G Car.
5G Car, okay.
So just Google on 5G Car and you will find the website. It's a 2-year project and we run 1 year now. And there are a lot of use cases there. And I would say the most advanced will be remote driver, remote parking. So it's not, it should be an enabler for autonomous vehicles in massive scale, but personally, and the European industry seems to think that it's a little bit further away. Yeah, it's what is the unplanned statement now. I have a 40 minutes presentation in my pocket.
Oh, okay. Well,
actually,
sorry, put you on the spot there to give a quick summary.
I think also, I was also in a panel at the UCNC a couple of weeks ago, this European conference for all EU projects, and my view there was that maybe you should have split focus. In the public space, regular cars driving in cities with a mix of manual cars and pets and kids and bicycles and pedestrians that are blocked with headphones. It's quite complicated use case. So why not? So there maybe we should have, maybe that's, Ted shows the hype curve. I think that is a hype curve problem. It will take 10, 20 years before we have it fully autonomous in a massive scale. But there are a lot of other use cases in professional contexts. Harbors, mining areas, building construction areas, factories for store warehouses, sure. automatic robot cars in warehouse, high-build warehouse storage. They can be fully autonomous. And there we really could play with control network assistance and learn what we can use 5G and beyond 5G for. And then we are ready to go massive scale in network-assisted autonomous vehicles. That's my view.
Okay.
Millimeter wave will play a role. Just as a comment. In street canyons, I think millimeter wave have a good fit.
Yeah, you need to distinguish, between connected cars and self-driving cars. There are two very different things, right? And was another IEEE event a few months ago, and someone from Berkeley made it very clear. Self-driving cars, you mean totally autonomous, able to drive wherever and in any condition. That's going to be very far into the future. Now, connected cars are useful, but they're not by any means self-driving or anything like that. Now, the second aspect is that applications for connected cars, because cars can talk to each other or to a network, may be very different in terms of importance, in terms of requirements. Clearly, safety-related applications, typically short messages, low latency, high reliability, versus entertainment for your kids, so they don't bother you. That's a different thing. So where is 5G millimeter wave playing a role? Well, high data rates can help, in both the entertainment, but also in some safety-related, like LiDAR images are very heavy, and so there is a role here for millimeter waves, I think. Although, how to make it work in a highly mobile and highly dynamic scenario is, of course, a challenge, right? So we're actually doing some work in this area and trying to find, what are the fundamental limits.
Yeah, I think the current EMBB for millimeter wave definitely solves the infotainment needs and the HD map needs, and it makes a lot of sense for a car. And I agree that there's high mobility, but if you look at some ways like highway, New Jersey Turnpike, or some places where they've already cut down all the trees, and it's a clear line of sight, and everything's very predictive. You can predict that the car is coming from there, and then next step it will be, you can track the cars fairly easily. It's a very predictive environment. But the problem really with the connected car in that use case is really that the car industry moves very slowly. And by the time they adopt something like that, it's almost unless there's some kind of a mandate, it's very hard for those things to happen immediately, right? Because the operators will not deploy base stations for that use case, because the car manufacturers will move slowly. They'll focus more on the UE handsets, and it'll take a while before those two things converge, and that connected cars, there is infrastructure for connected cars on highways, unless there's a mandate by a government mandate, and then they, all the industries, join together.
What's the state of DSRC now? I mean, in terms of deployment. What's the state of DSRC in terms of deployment? I mean, even that standard's been out for a number of years.
Some car manufacturers announced they will deploy DSRC in all their cars, maybe from some level up soon. And so that's happening. I don't know if it's mandated, but it is happening.
This panel is putting me to sleep. And so, so what, so for everything there's, so I've heard, that, hey, we need to do some more fundamental research. And then, for latency, yes, there'll be a physical problem, but let's classify where. So are there use cases? So I'm just trying to put some structure here. So latency, is it, Palmer said, well, we've been trying to make things lightweight for a long time, but TCP/IP, is embedded everywhere. Yeah, we're not going to replace that anytime soon unless we make a very darn important case. So what are the applications where latency is going to be an issue? And then we have to address the question, okay, physically, what are the limits? We can put radius in terms of, speed of light, and that'll give us the first thing, and then what kind of networks can be within it. So can we put some structure on the kind of research problems that we can address? And do we have enough information? And how does industry, industry, it seems like, there's just onto robustness. So what is there something to collaborate, or is it lost cause? Seems like it's a lost cause. This is the fourth meeting on RCN, and NYU, you guys have a lot of the affiliates, but I don't know how much, your comment was yesterday, yeah, we listened to you guys initially, and then we went and did our own thing. So, what are we, can we, what is the role for collaboration here? And what, are there some problems that we can identify where we can, whether it's theoretical or whether it's, if it's end-to-end simulation tools that you're developing, what is keeping them from being predictive so that we can actually help address those fundamental questions, or maybe explore some from scratch protocols to move things forward? I mean, it seems like we are just, passing the buck to some other domain where, putting the blame somewhere else. So what are we willing to do to push this forward?
In terms of application domains, I mentioned two good candidates. One is automotive, right, where low latency is needed. Because
what you earlier said, there'll be some physical limits, right? So why is low latency limit needed, and what kind of information? And
if you look at safety-related applications in the automotive domain, where you mostly talk to your neighboring cars, which are very close, and so the physics limit goes down, then that may still be feasible. The second application scenario where I think this is going to be important, and the scenario itself is going to be important, is industrial IoT. Right? In everything where you have a control or automate the process and tightly control things from a safety perspective, but also from an efficiency perspective, the timescales in those environments go down significantly. And so that's another area where low latency will be important. And again, it's a local environment, and so probably the latencies will be because of how you design your communication system, not because you have to travel 100 kilometers. Right?
Yeah. So what about those, different dimensions? I don't know which company has that, 5G different latency rate. What are maybe some of the pain points? Maybe we need to look at some extreme cases and use case and kind of look at where those applications would come in. This kind of thing, but there's another, I don't know, maybe Nokia had that where there's like different dimensions like latency, complexity, and things like that. Maybe that's what we focus on, or some use case.
So one thing that maybe we need to investigate is, I mean, clearly in the back end, replacing TCP and IP is going to be much more challenging. But we may be able to now, because of the way it is, have the gateway in between that has a different network layer protocol for the last mile or the last hop and a different one on the network. I mean, IPv4, we kind of, it's death knell because of address space, we kind of solve by putting the NAT boxes all over the place, right? I mean, same way, I mean, now maybe it is a time to think of these other boxes that will do the gateway between two network protocols. Because for the AR, VR stuff, maybe it is just like local thing, and we could achieve the latency that is there, and only for these end-to-end applications that we need to go to IP and TCP, and maybe a network gateway that translates to these two protocols, maybe a solution that we have to go for to achieve both latency while retaining the legacy of TCP and IP in the back end. And then we need to investigate what would be a suitable network and transport protocol just at these UEs and just at the last half of the millimeter wave, or just basically more generally these high data rate wireless networks in general.
So can I intervene? So my comment here is we've done exactly what you're talking about in the millimeter wave specifically. So reconsider the proxy server solutions to maintain the TCP/IP semantics while designing something more cross-layer in the last hop, and we have some really good results. It's based on the simulations, right? So it's not we need better models, but we're taking that direction. And my question is, how can we make an impact? Because we're clearly working on that. We're trying to, capture the most realistic scenarios, but we would like to have a better impact, and we don't see a way to engage. What should we do? Go to IETF? Should we, because otherwise it's this constant, academics publishing papers that just remains in the academic domain and have zero impact. I would really like to find a way to have a stronger impact.
Into the 3GPP standards or into the industry, like the automotive industry, both of which are kind of very difficult?
Yeah, I know. Exactly. I mean, in any sort of, like how can academics developing and having these open communities, research thoughts and brainstorming, how can we have a bigger impact, and that does not remains, in our papers. And one more comment, always related to this TCP stuff, is recently the head of system architecture at 3GPP had some interactions with IETF to reconsider the TCP/IP stack and considering new protocols, like for example Google Quick protocol. But those are the Google people. How can we, have our say and show our results? I would like that. That's something that we would like to. But we need better models. We need better test beds. We need we need to refine all these tools that are giving us some insights about performance. So yeah, these are my thoughts about that.
Do companies care about this? Do companies care?
No, so this is. No. They don't care until it hits their bottom. And so I was having a discussion with Shiv yesterday too, right? That, okay, so the first thing is you have to think about, okay, what is your message that you want to convey? So I again go back to latency, right? I mean, that's nobody discusses. Industry people also, you also said, hey, there's a different part of Qualcomm that works on that. And so maybe we haven't hit that use case, right? And so what you need to think about is, okay, what are the, with our existing standards, with the 3GP work, what are the scenarios where that latency is that was my question to you a year ago. What are the situations where, a millisecond latency is going to be critical, or where the current protocols will just not work, and it would hit industry in their bottom line?
Cooperative flight? Cooperative flight? Cooperative flight?
Cooperative flight? Well, where is it happening? Yeah, maybe. Whatever it is. I think we have a couple. Yeah. Go ahead.
Okay, all right. Basically, I have to.
Where are you going? Italy, back to Italy, or
No, California, LA. Yeah.
Are you ever in Italy?
I'm based in Italy.
All right.
Thanks, Miguel.
Yeah. So I had like a kind of more industry-related question. So you guys have kind of got the operators to buy in 5G now. It seems like it's going to happen. So if 10 years from now you need to sell them 6G, what are the things that you have to show to them to convince them that they need to actually buy into a new environment? Is it just improving capacity by another 10 to 100x? Is it getting rid of small cells and actually making macro cells that are capable of these high capacities? Like, what kind of features do you think justify the next steps?
Actually, a big part of the deployment, if you ask operators right now, many of them don't really have a capacity issue at this point, but they think that they will have a capacity issue. So it seems that 5G will solve that. It also brings in more revenue for operators because there's all the new services that it can bring in. But a big part of it is just large operators that push forward. They want to be the first in 5G and they want to deploy it, and they know that revenue will come in. They know the demand will grow, and then at that point, the others, it's almost peer pressure, right? You can't have one operator doing 5G and then no one else is interested, and then now other regions start coming in. Europe doesn't want to be left behind, and everyone jumps on the bandwagon, right? If you looked at the early schedules of 5G release, it was further out. It wasn't meant to be end of this year or next year, because that's really when people thought that the capacity needs would be there and that they probably have to think about deploying 5G systems. But because of some operators pushing it earlier, now the whole world is behind and they all want to deploy early on. So I imagine, it's hard to predict what things will be in 6G, because even it's not clear what the need is for all these in 5G. But in 6G, maybe there will be more capacity, or likely that we will need more capacity, and again, there'll be another push by operators to deploy 6G and try to get more revenue streams and think of more use cases. But it's hard to predict at this point.
Mickey, did you want to say something? I forgot. Yes. Okay, I didn't see if you were raising your hand or not.
Yes, thank you. So it was related to your earlier question about does industry care about some of the simulation tools?
Mickey, by the way, is from InterDigital. Sorry.
And I think from our standpoint, for instance, we play in the field between academia and commercial deployments. We're smack in the middle, developing technologies. With our focus on 3GPP, for instance, we would have been extremely interested in having the NS3 network level simulator available and ready to use for instance, the NYU study item on release 16. But obviously, it's not there yet. It's going to be very interesting in the future. But it could have been available for this good of mankind kind of contributions that would help develop the NRU standard in release 16. So yes, in that respect, we really care. And you know that we work with UPadua, for instance, on related topics. So that's an area where we could quite well.
So why wasn't it ready? I think so. This is exactly the thing.
It's not ready for readily available for NRU, right? So NS3 has a lot of LTE functionality and capability, but because it's being developed while the 3GPP release 15 was being specified, it is hard to have it available at the same time.
So is it impossible or is it a resource problem? Because if it's a resource problem, this is a perfect place where industry and academia could, and you should put your money where your mouth is and say, hey, Marco, you want to expand your team so that you have this NS3 simulator ready for prime time?
Sorry, we've been, Marco can talk about this, but I mean, it is a bit of a resource issue, and we've been trying with Sumit to address exactly that.
But this is exactly the case, right, where it would be where industry, you know, there are things in industry which they don't have the time, and there'll be a place where it could be useful, and I think it's true across the board, but people are just too busy to even think a little bit, yeah.
So, do you want to talk just quickly about discuss with Sumit and Pantelis almost?
About what? Which one?
NS3 and trying to get it.
Yeah, and even more in general terms of, Sumit is the maintainer NS3. Yeah, which were basically. Yeah, so we would like. I think there's a call for you guys at NSF. Basically, we're trying to find a way to get funded for growing these, growing.
Industry should fund. No, or Qualcomm. I mean, who are you? You are smack in the middle, right? You said we are smack in the middle. So you say, hey, this would be useful. You convince your industry players that, hey, this would be useful. Let's provide the money. I mean, come on, when we say government should subsidize industry, that's ludicrous. I mean, let your CEOs and CTOs take a few 10% cuts before that.
I have a maybe it's not even about you guys invest, but why don't, I'm pretty sure that, I know for a fact that there's a system level simulator at Qualcomm, there's a system level simulator, I guess, at InterDigital. Why can you share the baseline? The baseline. We don't want the technologies. We don't want IPs, but just the baseline, the L1 baseline for link level simulations, or the Mac. What's that?
Okay, because obviously there's a lot of work that was put in both the NS3 simulation, network level simulation, as well as in InterDigital's system level simulation, right? So I think the collaboration would be extremely beneficial if somehow resources would be thrown into, more resources would be thrown into the NS3 to bring it it to the level that we are at. We obviously cannot disclose a lot of our internal stuff.
Yeah, no, right? Exactly. But the baseline, there's so much baseline.
Okay. So can this be an action item for follow-up? I think this seems like this is similar to the testbed stuff where community, there is a, this working group has been moving things along. You have put yourself in the middle right now as well. And so, let's you place, InterDigital isn't smack in the middle, so this should be an action item to kind of say, okay, what can, and you have some good questions, what can industry share, and what are your needs? How can academics help who are interested in that, and what is going to be needed to fill in those gaps that you're seeing? We need to improve models, channel models, measurements, whatever it is. This could be another action item for a plan, a community plan for a subgroup. And this could, I see it as connecting to testbed too, because measurements could go in there, obviously, and other aspects too. So I think this could be something that we could follow up on. So even though you said no to the panel, you're on now.
Actually, I'm going to, because we have about maybe 10 more minutes. So I had walked through a couple of different use cases, but I wanted to bring to this one just because maybe on Akbar's point about trying to get actionable action items out of this. So one of the use cases, of course, is on edge computing, and this is particularly relevant today with all the talk about AI. Maybe AI is in the peak of the crash and will crash. But one thing I noticed when doing a research for this panel was there's actually presentations you can look on the Amazon AWS services, for example, and they have talks about 5G, what 5G will be for edge computing, but I have never seen any of them show up, not just at RCN, but pretty much any of the wireless conferences that we're going to. How do we engage with this group? Because presumably, either maybe there is no relation between 5G and edge computing and AI, or there is, but the companies that are in that space are just not talking to us. And how do we get this? Actually, this was stolen from I forget one of the another cloud provider. It's not the Amazon's, but the Amazon has whole presentations which they go out and give to other AI companies on their, on the AWS services and MXNet and so on. So maybe has anybody had experience relating with Google or Facebook or AWS, and can we ever get them at an RCN? Should we get them at RCN?
I think that's actually an excellent point. I'm glad you brought it up because I think there's a lot of so machine learning is everywhere, right? So on the NSF side, we see machine learning on all the proposals, AI and whatnot, and nobody knows how it's working. And one of the places where I think from a basic science perspective, it's very useful is to understand how AI works in engineered systems. And this is a perfect example where I think, networks are going to be running a lot of data analytics on their own. It's like self-referential AI. And I think it'll be great to bring them along, and maybe, maybe InterDigital or Osge has.
Actually, I do know that Qualcomm has I met them actually at NIPS, the machine learning conference. Jeff Gallagher, who we used to work with, I met at NIPS, the machine learning conference. So there is, I know, on the terminal side, looking at AI, but not in terms of necessarily in the connectivity part. I don't know.
Yeah, that's great. I mean, we do have a group that looks on the terminal side, because at least on the terminal side, I mean, for years things moved to the cloud, but now there's so much compute power on the phones, and that there are applications of AR and VR and machine learning that they has to happen with very low latency on and can use the phone. Those groups, I can engage with those groups and see they likely do work with Google and Facebook and others.
Edge computing is going to be key to low latency as well.
Right. Yeah. That will be a real driver.
Yeah. So I think we need to bring that. Yes.
Manu?
Yeah. So one, again, the community that you're talking about and access to them. So we've had a lot of interest from our power industry consortium members, namely Intel, as well as some members in the telecom infra project. So there is a working group within that community looking specifically at AI and machine learning at the edge as it applies to telecom networks. What they're looking for is data. I think the struggle there has been access to operators and willing operators that will actually run AI and machine learning and actually provide that data. So they've come to power test beds to actually see if some of that operational data can be shared so they can run their training data sets on the back end. But again, would be happy to make that connection, and they'd be very willing to come out here and speak with us.
Yeah, there's definitely interest that, from the data side, like people want to do data analytics on the network itself, but also you look at the presentations that AWS is talking about are providing cloud computing offloading for AI. And, I just don't, and they, like I said, they see 5G in their presentations, but I've never even ever seen any of these people at any of the conferences we're at.
No, I think that's an action item too for next, for your own. Have you had them at the Brooklyn?
No, I've never seen them.
No, I think that's a good action item to get them engaged, because I think that to me, the latency is one part that gets shrugged under the rug, and this is a key enabler and AI related. So I think that would be a very good thing to bring in.
Yeah, just one comment. First of all, as Manu said, a lot of discussions, even a few days ago in San Francisco in the IEEE World Forum, talking about this and opening, because we need data to make machine learning. And the second thing I want to bring up, and it's basically an open invitation to Samsung. I was talking with some people at Samsung, and they want to do AI in NS3, basically. So this is also another unbiased comment that I make about NS3, and we'll try to bring them in specifically for this, and then we got also expand a little more on the core network and stuff.
Okay. Still one more question back.
They're wrapping up, it's fine.
No, it's fine.
No, so, another thing maybe for the next RCN meeting, Akbar has been asking what are the applications, and we didn't get too much response. And I think even the testbed thing, Manu's thing was, we were talking about the applications. So NSF had that on the wired side, for the gigabit kind of thing, after Google Fiber and so on, NSF had the US Ignite initiative to fund applications for gigabit applications, basically for the end-to-end, but more distributed across the country, right? I mean, they're focused on undoubtedly, and some smart cities and those kind of things. But maybe we do need to engage either the US Ignite community or have specific calls from NSF to think about applications that will drive last half gigabit, multi-gigabit wireless backbones, right?
True.
I mean, applications. And maybe we can have sessions in RCN trying to target those kinds of things in here.
I just want to, so basically the next two power platforms are actually envisioned to address that. So it's again a shameless plug for the upcoming RFP for the next two platforms. So if you are interested in building a platform that's more application industry vertical focused, because that's the feedback we are getting from industry, is to focus on applications, use cases to drive the technical requirements. And that's something that we are addressing in terms of funding the other power platform. One initiative I just want to mention, it's not a US-based one, but it's in Canada. It's called ENCOR, ENCQOR. It's a $400 million initiative between 5 telecom operator and infrastructure companies and Quebec and Ontario provinces, where they're actually doing exactly that, funding SME startups, companies to come to the table, developing a 5G network and actually having them develop applications to sort of stress test and see feasibility. So again, it's happening worldwide, and I think we want NSF to hear that too.
Seems like another place where industry academic collaboration could be brought to the fore, because I think this is one of the goals of PAR program and also RCN, to have a better collaboration with industry and academia. And personally, I think we haven't really, in RCN, we get a C for that right now. We haven't really made any progress on that, so maybe some of these things would lead to that, where industry and academics can collaborate, especially for things which are aimed at particular use cases which are of interest to industry. Okay.
All right. I think we're kind of running out of. Maybe we'll just wrap it up.
We have time. I just wanted to, and we can still discuss. I wanted to, if you want to have some closing for this one, but I wanted to loop back briefly to the test bed.
Yeah, so I think maybe we'll leave time for that. So why don't we just wrap this up there? And I think so there were a couple of other things I wanted to talk about in this panel, but I think it might be better to talk about them in the context of the test bed anyway. So we could just go straight to that discussion. The one part I just wanted to, the moonshot part, I guess, how do we think about connectivity, and we can think about this maybe offline. Right now we maybe just use our phone for either text or calling, but what would it take for us to have this meeting virtually and not have to travel here? And part of that's a connectivity issue, and are we, can that be a moonshot view of this? Anyway, I'll leave it this, because I think I'd rather leave time to go back into the nitty-gritty of the test bed. No, it's fine. Yeah, do you want?
Of interest to NSF too, because we do virtual panels. And so we use this Blue Jeans software, and it's actually pretty effective for the most part. But I think that could be a moonshot, that how good an experience you have with a virtual augmented reality. Yeah.
Okay, so why don't we go back and give time back for the president, or maybe you take a couple-minute break and then we'll go.
Let's take a couple of minutes break, and then we'll start about 5 minutes to discuss a little more about.
All right, thank our speakers.
Yeah. You're the last man standing. Yeah, no, I think he was going to come, but then he said, "Oh, no, I'm sorry, I had scheduled something." Yeah. So hey, thank you for coming.
Yeah.
Well, hopefully you can stay a little bit longer.
Yeah, I
or
can
not?
stay a little bit longer.
And so you are on the steering committee now. I'm pretty sure that I had invited that hey, so on the steering committee as well, right? So, yeah. Okay, good. So I was also hallucinating. So yeah, thank you. And
send me a message.
And so yeah, I think next. And yeah, I want to. Some of it has been. We have been. So again, industry academic collaboration is significant, and anything.
Ladies and gentlemen, if you could just grab your seats, we'll get started in a moment.
That's okay. No, you should be here.
Where's Manu?
Manu? Yeah, yeah. I mean, they can, I guess, yeah. All right, folks, it's the last. Oh, there's the emulator man, which is really a simulator with the hype cycle. We are in the peak of the emulator hype cycle. Okay, so we have about a half an hour discussion wrap up for the community testbed development aspects. And so I know that, so just again to refresh your minds, there are, in RCN, the interesting problems have been at the interfaces. So there have been working groups, especially in networking and signal processing side. Marco and some other folks, Ismail, and even some of the UW folks, Seattle, Tom Henderson, have been really looking at that, and they have been doing end-to-end simulation, a lot of work, interesting work going on there. And then there's been more recently hardware signal processing that has taken traction. And so yesterday the idea came that, okay, there's a different groups out within the country in the U.S. are developing these test beds. Berkeley, Wisconsin, and I know that Jananth at CMU, he's developing some, and I'm sure there are other folks. And some are building the whole thing, others are taking eval boards from, Velocity, Qualcomm, wherever, and you're just playing with networking protocols. And the idea here is there an interest to have an end-to-end simulation, or not simulation, a testbed platform, which could be, I don't know how it would look like at the end. It could be in one place and it's accessible like a mini version of PAR or whatever, or ideally at a cost point that can be replicated in a modular fashion at different institutions. And so the first thing is, what we want to gauge is interest, and two, who are the people, who are working on, RF, and then ADC, FPGAs, because you'll need that, and then the networking protocols. And who would be the people who would be interested in actually building, involved in being a part of a team that actually builds, creates the specs for it, and builds that test bed, and then who would be interested in using it at the end, and then eventually it could also go into, provide technology for power platforms. So, so first whoever I want to hear from folks here, how many people, are there any people involved in building it, and who would be interested in using it, and so on. So I know that there's you.
Hi, so I'm from India Networks Institute in Spain.
Okay.
So we have like 2 different tracks right now. So on the one side, we are working with off-the-shelf devices. So using 1180 devices with the Qualcomm chipset. So with these ones, we are just doing we have the whole protocol stack. So we are trying to do some reverse engineering in order to be able to obtain data and also modify beam patterns and these kind of things. But of course, it's very limited. We cannot do whatever we want. And on the other hand, we are building right now, we bought a large FPGA and also an antenna array front end of 60 gigahertz. And we want to do a platform with that. And we are trying to do this as an open project to be able to collaborate among different institutions.
Very good. So you bought an FPGA and an antenna array for 60 gigahertz.
Yeah.
Where's your antenna array from?
So we bought the one from Sivers IMA.
Okay, it's some European.
I think they are from Sweden.
Okay, so it's a single beam phase array, 60 gigahertz.
Yeah.
Okay, and then you're developing FPGA solution. All right, very good. So you would be interested. You would be interested in being part of some development like that. And so do you think your expertise is more, it seems like more on the FPGA and algorithms part, or?
Yeah. Yeah, not on the other side,
okay.
for sure.
Okay, very good.
More like a networking group.
Networking group, so you can, and do you think you're interested in developing real-time implementation protocols?
Yeah.
Very good, excellent. Excellent, so we need to get your name, absolutely, and contact. Who else? Aditya, are you interested in building something real?
Well played.
A real emulator?
No, so the project that we are running right now is to build a 28 gigahertz array, a fully digital array. So we are basically building these boards that have 4 channels each, and they are extremely small, they're going to be 2 cm by about 5. So you can tile them to create arbitrarily sized, rectangular arrays. And so we are working on fabricating this board, everything using commercial off-the-shelf ICs from analog devices and a bunch of other different players. And so, we are still very early, but we hope that by the end of the year, we'll have a proof of concept, fully digital array at 28 gigahertz working. So
28 gigahertz fully digital, how many elements?
So the thing is that every daughter board has 4 channels,
Yeah.
but you can tile multiple of these daughter boards arbitrarily in both directions to create hopefully arbitrarily sized.
Okay, so it's like so you have a basic module which is 2 by 2, 4 elements, full ADCs, DACs, and everything, and power amplifiers and everything in there.
So the board that we're designing right now is actually, it goes, say on the transmitter side, it's 4 channels IF in, and then some reference LOs, and then you multiply the LOs up, and then you mix, and then you filter, amplify, and then you connect it to antenna ports.
Yeah.
And then on the other side, the antenna is going to, so the daughter board has IF in and antenna ports on the outside, like these really tiny SMPS connectors.
Okay.
And then the antenna board on the other side is going to be like just is going to have either patches or Vivaldis or whatever with connectors at the bottom. So you can just like click the antenna on top of the daughter boards.
Okay, very good. So you'll have, so this will be a modular, you could scale it up.
Yeah,
so that's
exactly.
fantastic.
So if you want to scale it up, if you want to have a different number of channels, you'll only have to redesign the motherboard because the motherboard has slots for each of the daughter cards that goes in. So you have to redesign the motherboard. So the motherboard is going to take in baseband IQs in, convert to IF, and then feed the IFs into all the daughter cards.
Okay.
And the reverse process takes
Okay, and so this is basically just RF, and you'll have IF interface, and then we can put it to the back end ADC. Very good.
That's it.
So,
I mean, we have nothing working, I must say.
oh, that's okay. We know that. I mean, we'll make it work.
And so, and I'm the engineer, so the probability of failure is.
High. All right. No.
It's quite significant.
No, that's very good. No, that's great. So you're in. So so that's great. You'll be another RF player. Potentially. So that could. Hopefully.
But we're new to the RF game, so, take everything
I think this would be, there's a lot of collective expertise
So
on that.
I wanted to maybe talk about two initiatives that I've heard about, but I don't know fully the status of them. On the network layer stack, there's out of Raymond's group, the OAI from France, the organized for open air interface. Okay. So they've already built a full new radio stack, but below 6 gigahertz. And my understanding is that there's some effort already to try to use that above 6 gigahertz, which is actually the protocols don't change that much. You just have to speed it up. So hopefully that can cover the upper layer stack, let's say Mac and above. And then I've seen this. So does anybody have much experience with the MathWorks side? Because MathWorks did provide an LTE.
MathWorks?
But the way that you could put the whole blocks on the LTE part and then simulate and then actually synthesize from that FPGA code, right?
Beautiful, yeah. I think this is something I'm going to loop back with them because, yes,
I know they have a 5G effort too. And I know, Mickey, you would talk to a little, have a little experience with that.
MathWorks, we will loop back with them because you can create HDL code from MATLAB.
Basically, we are evaluating the 5G toolbox from MathWorks to using exactly that, the HDL, to go from Simulink to HDL directly.
Beautiful, yes. So, so I think I wanted to get MathWorks folks here, but I just didn't get to do it in time. So we'll loop back with them. So how has your experience been so far?
It's in beta, so basically we're working on it.
Okay, good. So we'll keep you in the loop too, because I think that could be useful. Because I think I can share, in our group, we were working with Xilinx boards, and we use Simulink as well, and their system generator as well. And in the end, in some cases, you have to just code it up yourself, or system generator works quite well too. And Simulink is good, but when you come to tricky timing stuff, it can run into trouble. So, but I think MathWorks may be interested in putting some resource in it too. So we'll loop back on that. Cool. Okay, Hang. So who's Ismail? You're taking. Okay, so yeah, very good. So all the players, let's keep noting. So, okay.
So we are more focused on network stacks. So we have a project with the Army right now. So it's not related to millimeter wave right now, but what they want to do is to use 3GPP stack, but use their own radio. So basically what we are doing is we use OAI stack, all these LTE stack, and PDCP, all these things, but combine it with EMU. So this EMU is this Army research simulation or emulation platform. It can run on the multiple virtual machines then connected by the Ethernet. But underlying radio, So could be any radio, and right now, we use a wireless LAN radio, but on the top is 3GPP stack.
Okay,
so,
and this is also for real-time implementation.
So they don't have real time right now. So requirement right now is, but you can run on multiple machines to set up this simulation platform.
Okay, so I think this could be. I wonder if that is more tied into something like NS3, or would it go into some testbed where we would want to. So testbed, it's another thing I want to emphasize, and this was one of the, and I don't know if Kate is still here or not, but there's also this channel measurement, right? So once you have your testbed, you have a channel sounder too, whether you like it or not. Channel estimation, and you can do all sorts of channel measurements. So there's a non-real-time operation used too, where you just get traces and you can process. So everything. So you could be, so you'll be a good player for the networking protocols.
Yeah, I think this is one step further than NS3. NS3 is a more event-driven simulator, right? But this thing, the email is also a simulator, but somehow you can set up on multiple machines. The underlying, you can use Ethernet to simulate, put something to simulate the channel, and also you can plug in different radio. So right now we just use wireless LAN, because that's already built in.
So is that email? Is that an army thing?
Yeah, I think email is one of the simulator came out from Army research or Navy research,
And it's open. They are willing to share.
That's also open source.
Okay, okay, very good.
Right now they have a very simple built-in ad hoc wireless LAN based thing, on top of that. So we are trying to integrate OAI stack, the IoT stack.
Is that the same one that Sandeep was mentioning, OAI open air interface?
Yeah, right, yeah. But OAI is right now is running on USRP platform, So we are trying to do is to take out the radio part, but put any kind of other waveform generator in. So because they call the sim layer. So the sim layer, you can build some adaptation, things. So.
All right, very good. So I think we will, you'll be on the networking side. All right. Who else? Yes.
Recently, we were working on.
Say yourself what your name is.
Okay, Ahmed Suleiman, Embry-Riddle Aeronautical University, Arizona. A few years ago, we were working on spatial modulation scheme. And there were a lot of theoretical, input on the scheme, but no one had, presented a result from test bed. So what I did was to bought some off-the-shelf warp board developed by Rice University, and we were able to put this work in 2x2 MIMO. We extended it to 4x4. And we were able to collect some real-time data from this to show that this system actually works. So this was an example of, MIMO-based or spatial modulation-based testbed. I developed it. It works at 2.4 gigahertz, and we could also go at higher frequencies, just about changing the antenna.
Well, I think so. This is actually a good point, but warp boards will not work in this. So this is like building a warp board, version of warp board for millimeter wave. So warp sampling rates are not going to be fast enough. So that's why you'll need a dedicated FPGA development. And this may also be true for some of the networking protocols. It's non-trivial because your data rates are very high, so we'll have to think about, conceptualize, what that architecture looks like. But yes, so this would be developing a new warp board.
Okay. So on the RF side, like I was telling you, channel sounder is all about just, one can build them oneself by putting local oscillator, signal
Yeah, well,
generator,
that's exactly what-
transmitter, receiver, and you can choose the frequency as much as you want.
Yes.
Now, developing that into MIMO is also possible. Right now, we're using one transmit and one receiving antenna.
Okay, so you could potentially contribute to the RF part too, because one of the things is that we have discrete solution and we could, and there's different front-end architectures that could be integrated into an integrated RF board, which could be used. So, you know, for example, Wisconsin could provide lens arrays for beamforming, and, you know, Berkeley could have phase arrays, or Aditya could have a phase array on steroids. Fully digital beamforming phase arrays. Okay, who else? Ismail, yes.
So I think we have a couple of platforms that can be of relevance. One of them is, maybe I can speak also for my collaborators. We have a project from NASA with David Matolak and Hanimer Puyan from Boise State. So we are developing channel sounders, which will turn out to be also some test beds at 3 different frequency bands. What we have at NC State is PXI-based platform, which we already started doing indoor measurements. We have a lot of, we are collecting data. These are for now based on horn antennas and physical steering. We are looking into now moving outdoors. We have our FCC license at 28 gigahertz for a year. And Hani already is doing measurements at 60 gigahertz. He has a Keysight platform at Boise State, and David is doing 90 gigahertz from Rode Schwartz. So we will have 3 different platforms. The main idea is we will go to airports together, and we will do experiments in the same exact environment to see how the propagation, they change in these 3 different frequencies. We are interested to do air-to-ground scenarios, but that's not easy, obviously. But like I would like to echo what you said before. Once you have these test beds, you can use them as channel sounders. If you have a channel sounder, you can use them as test beds. We are also looking into using our platform for drone detection. I don't know what will be the range and how feasible it will be, but we also had some tests for example, indoor mapping. We were trying to map the size of a room in an indoor environment. We sent a white paper to DoD, but it didn't go through. So that's one platform we have. We have the 2nd year funding coming, so we are looking into what phase arrays we can integrate to this platform. We are trying to get a quote from Anokiwave, but we have been not successful.
Good luck.
So if there's any of you have expertise on or suggestions on phase array platforms for integrating to NI, that would be very helpful for us. We also have a USRP-based platform at 60 gigahertz with Pasternak, Rubik. We also have some measurements. It was the main motivation for developing that was carrying them with drones. So there was a poster yesterday from NYU. We have to, for one of the projects, we have to do air-to-ground measurements. And recently we started looking into doing an FPGA-based, I mean, I don't know if you want to talk more about that, but with a master student, whether we can do it with FPGA, I'm not sure where it will go, but that's another thing we are doing. And the last thing is we had evaluation boards from TensorCom based on 11AD, but what I understand is they are shutting down or going out of business, so one of them stopped working. I think they were very reasonable for doing air-to-ground measurements. The range was up to 500 meters, but we couldn't do air. I mean, they stopped. We have a paper, simple paper in VTC coming up based on the measurements with those. But so those are some platforms we have.
Okay, so that's great, and I think that actually brings up another point that people who have already invested in. So one point I want to clarify: if you have a test bed, it's also a sounder. If you have a sounder, that's not necessarily a test bed, because sounders you cannot test all the protocols. So it doesn't necessarily go the other way. So for example, people who have already invested in NI equipment, right, they cannot do networking protocols where you say, hey, you can put it whatever you want. So with your PXI, if someone built a FPGA-based networking interface, you could use that, for example. So I think, and then the front-end RF could be useful for you too, just like you said, phase array or lens array that you could use. So I think that's the modular part that could be really useful here. But where would you think your main contribution would be? In processing or developing networking protocols and FPGAs, or where could you contribute? Or maybe you'd be the user.
I mean, it can be user, but when you say test bed, this is a communication test bed all the way going to networking layer, or can you consider, for example, we are
what
also
I'm
interested in sensing localization type of applications in indoors, so test bed can be many different things, like it's not necessarily networking test bed.
So that's a good point, and I think what I'm initially thinking is end-to-end communication with real-time implementation of protocols, where you could play with it, and it could also be, for example, I can just, our plan for Wisconsin has been to create these access points with beamforming capability and then put them in different buildings and create a virtual network of 3 or 4 access points, and then put you mobile devices or mobile stations accessing and creating networking protocols. So I think that's what I'm thinking, which potentially could be replicated. But this will be fleshed out as we go along.
So it's also, one other thing we are thinking is we have right now, it's obviously channel sound or unidirectional, but if you have 2 more pairs, one more pair of millimeter wave radio heads, we were thinking of extending it to bidirectional, then it becomes you can do uplink and downlink communication. So that's also.
Yeah. Okay. Shin?
So far, we mainly work on the implementation or just simulation on the MATLAB platform. We implement all the channel models and also 11 AD and AY kind of protocol stack. I think we can extend to the testbed. The reason is testbed has too many platforms. We don't know which one we can apply, which one will survive. That's a major problem. I think it's no problem. We can extend to FPGA kind of things. But really, we have to choose something will work, because you can see the different things. I don't know which one will work. But the protocol itself, a lot of cases, doesn't really depend on those platform.
Okay.
To some extent, the simulation part actually is challenging. You have to build something.
Yeah.
And for channel, for example, you can measure, but in order to do the simulation, you actually have to understand channel model to actually build it.
Yes. So I think you could, So that could be also the end-to-end simulation that Marco is doing. But I think that brings up another interesting point, where a lot of us will have simulation software in MATLAB. And I think if math works, especially if we develop it in Simulink, or maybe their HDL coder is even more advanced, so I'm going to loop with them. Maybe next time that's an action item for the organizers to have them here for sure, to see how much of that could be transported onto the FPGAs. To create an HDL code. But some of it would be non-real time, some of it would be real time. Okay, so we are, Marco, yes.
This is something, I met these guys, ITRI, I don't remember where, from an Asian. Yeah, right? What's that? Yeah, exactly. And they have a platform, a fully MATLAB-based integrated. It's very interesting. I think,
actually, I know the team working on. They have a platform supporting millimeter wave communication. Everything is implemented in C and MATLAB. And now I think I spoke to them because I work on the OAI implementation. We're trying to create an interface to integrate OAI on top of their millimeter wave platform. And last time when I met them in June, OAI workshop, I invited them to join the workshop this time, but they are busy for MWC. But they definitely told me that they are interested in joining this community.
It's funny because I invited them too, and they told me that somebody else invited them. That was
I think that's me.
Okay.
Yeah.
And there's a very nice presentation that they public domain that I found that's from the OAI meeting. It's very nice.
Yes.
Yeah, so I think we should take a look. I will share.
Yeah, this is below 6 gigahertz right now with 56 megahertz bandwidth, but they could be a partner in helping us build some of the components.
Yeah,
very good.
It is because in Taiwan, the license band is not in 60. So they choose lower frequency.
Very good. So we'll loop with you too. Who actually, before I forget, that's also an interesting point that a lot of companies are also now putting out eval boards, including analog devices. And so we need to be, there's a lot of things that's available out there, and some of you will have information on that. Anybody else who wants to share who is working on test beds or would be interested in this effort. So if we had this available, how many would be interested in using it? A lot more. Okay. So I think what we're going to do is we'll definitely follow up on this because, and with a little more structured information so that we get information from you, get a kind of a mailing list for it, for a group setup, so that we can develop a framework, what this looks like and what the specs would be and build on it. And our goal is to, maybe have definitely next steps for the next meeting, which is 6 months, and maybe in the 6 months or a year at most. We have 2 meetings left, so at least at the latest, at the end of that, if the community wants to do it, then there should be a plan and the players identified. So, yeah, okay. Any other comments by anyone? Do you want to say anything, Greg?
I think this sounds like a good plan. I think kind of coming back together and making sure that whatever comes out is modular and has well-defined interfaces will kind of be the biggest key to success. So, if everything is kind of undocumented or just kind of ad hoc interfaces, one person might get something cool to work, but it will be like extremely hard for everybody to adopt. So we just need to be very kind of cognizant of that.
Absolutely. That's a very good point, and I think that's an excellent point. Yes, I know exactly what you mean. And I think, but the most important, the most beautiful thing about an RCN like this, and this is my experience first time with something like this, is that the collective expertise in the entire room. I mean, it's like for every interesting or important challenge, there's somebody who is interested and has the skills to do it. So I think that's what makes it successful. So it'll be a team effort. So thank you very much. And well, I want to thank the local hosts again, Sandeep, and I don't know where Pat is. Pat Donahue has done an amazing job. She's the one who's the chief organizer, and then William, who was the AV guy. I know today we have another person. Thank you. And also, where is Adam? Yes, thank you, Adam. So let's give him a hand of applause. Thank you very much. Next one is going to be in January, but we'll announce the location to be announced. Yes, lunch is in the back.